Most people think traveling faster than light is impossible. We've been told for over a century that nothing can break this cosmic speed limit. But what if reality is more flexible than we assumed? Scientists have discovered that space itself can expand faster than light, that time can slow down, and that the universe follows rules far stranger than our everyday experience suggests. Throughout history, what seemed impossible often turned out to be waiting for the right understanding. The speed of light isn't just about light, it's woven into the fabric of reality itself, shaping how cause and effect unfold across the cosmos. In this video, we'll explore whether this ultimate barrier might one day be crossed, and what that would mean for humanity's future among the stars. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now, let's get started. The speed of light sits at roughly 300 kilometers per second. That number might sound abstract, but think about it this way. Light can wrap around our entire planet more than 7 times in just 1 second. Yet even with all that incredible velocity, a beam of light still needs more than 4 years to travel from the nearest star to our own sun. These distances force us to confront something unsettling about the universe. Space isn't just big, it's so monumentally vast that our usual sense of travel, of getting from here to there, starts to break down completely. When we talk about crossing between stars, we're not discussing the kind of journey where you pack a bag and arrive somewhere reasonable. For over a century now, dreamers and scientists have wrestled with this same puzzle. Stories imagine starships that leap between worlds in moments, crews that explore entire galaxies within a human lifetime, messages that zip instantly across impossible gulfs of emptiness. The idea appears so often in fiction that it almost feels normal, like something we should obviously be able to do. But the universe operates by its own rules. Light doesn't just happen to move at 300,000 kilometers per second by coincidence. That speed represents something fundamental about how space and time weave together. It's woven into the very fabric of reality itself. Einstein showed us that as objects approach the speed of light, strange things start happening. Time dilates, mass increases, energy requirements spiral toward infinity. These aren't just technical hurdles to overcome with better engineering. They're built into the basic structure of how things work. Yet physicists haven't given up entirely on the dream of faster than light travel. Some propose exotic solutions, things like wormholes that might fold space, bringing distant points closer together. Others explore concepts like the Alcubierre drive, which theoretically could contract space in front of a spacecraft while expanding it behind. These ideas require materials that may not exist. Exotic matter with negative energy density. Amounts of power that dwarf entire civilizations. Even if the physics somehow worked out, the engineering challenges stretch beyond anything we can currently imagine. There's something almost poetic about this cosmic speed limit. Light connects everything in the universe, yet it also enforces a kind of cosmic loneliness. Information can travel between distant worlds, but only at this fundamental pace. No faster, no shortcuts, no cheating. Consider what this means for any civilizations that might exist around other stars. Even their most urgent messages, their most important discoveries, their calls for help or offers of friendship would take years, decades, centuries to cross the void between worlds. This creates a universe where patience becomes a necessity, where any meaningful interstellar relationship would unfold across generations, where the very act of reaching out to another world becomes a gesture of profound faith in the future. Perhaps that's not entirely unfortunate. Maybe the universe's built-in delays force us to think more carefully about what we really want to say to the cosmos, about what messages are worth sending across such vast distances. The question remains open, though. Will we ever find a way around this cosmic speed limit? Will some future physics reveal loopholes we haven't imagined? Or will the universe keep its secrets, forcing all travelers, all messages, all dreams of connection to move at this stately pace that light has always maintained? The speed of light sits in space like an invisible fence, not the kind humans build with posts and wire, but something woven into the very structure of everything that exists. Scientists call it a universal constant, but that term barely captures what it really means. This isn't just about how fast light moves through emptiness, it's about the maximum rate at which anything can influence anything else in our cosmos. Think about cause and effect for a moment. You drop a stone, it falls. You push a door, it opens. These connections happen in sequence, one thing leading to another. The speed of light sets the absolute limit on how quickly these connections can happen across distance. If information could somehow travel faster than light, effects might arrive before their causes. Events could become tangled, scrambled, creating paradoxes that would make reality itself unstable. For thousands of years, nobody even knew light had a speed. When someone lit a torch, the surrounding area became bright immediately, or so it appeared. There was no obvious delay, no sense of motion traveling outward. Light seemed instantaneous, almost supernatural in its behavior. Ancient philosophers debated whether vision worked by light entering the eyes or by some kind of beam projecting outward from them. The first hints that light actually traveled came from astronomy. In the late 1600s, astronomers studying Jupiter's moons noticed something peculiar. The timing of eclipses, when these moons disappeared behind the planet, varied slightly depending on where Earth was in its orbit. When Earth was farther from Jupiter, the eclipses appeared to happen a little later. When Earth was closer, they seemed to occur right on schedule. The explanation was elegant. Light from Jupiter's system took time to reach Earth, and that travel time changed as the distance between the planets changed. This was the first real evidence that light had a finite speed. Scientists could even calculate that speed by measuring these tiny timing differences across the vast distances of the solar system. Once they knew light traveled at a specific speed, new questions emerged. Why that particular speed? Why not twice as fast or half as fast? The answer wouldn't come for centuries, and when it did, it would reshape our understanding of space and time themselves. The universe, it turns out, has some curious loopholes when it comes to faster-than-light phenomena. While nothing can move through space faster than light, space itself doesn't follow the same rules. The fabric of space can stretch, expand, even carry objects along with it, at rates that exceed light speed in a certain sense. This is actually happening right now. The universe is expanding, and the most distant galaxies are moving away from us so rapidly that the space between us and them grows faster than light could travel across that gap. These galaxies aren't breaking any physical laws because they're not moving through space faster than light. Instead, the space itself is expanding, carrying them along like leaves on a flowing river. This distinction has sparked decades of speculation among physicists. If space can expand faster than light naturally, perhaps it could be manipulated artificially. Maybe a spacecraft could somehow ride a controlled distortion of space, rather than trying to push through it in the conventional way. These ideas have led to concepts like warp drives, where space contracts in front of a vessel and expands behind it, creating a kind of space-time bubble that could theoretically travel faster than light. Even our fastest spacecraft today move at speeds that seem almost comically slow compared to light. If light were a jet airliner crossing an ocean, in hours, our most advanced probes would be like bicycles slowly rolling along a runway. The Voyager probes, launched decades ago, and still traveling toward interstellar space, move at roughly 17 kilometers per second. That sounds incredibly fast until you realize light travels at nearly 300 million meters per second. At our current speeds, a journey to the nearest star beyond our solar system would take tens of thousands of years. The distances involved are so vast they challenge human comprehension. Even traveling at light speed, crossing our galaxy from one side to the other, would would take about 100,000 years. That's longer than our entire species has existed in its current form. These enormous scales have a way of putting everyday concerns into perspective. A traffic jam, a delayed flight, a computer that takes too long to start up. All of these minor frustrations seem smaller when you consider that light itself takes over 4 years to travel from the nearest star to Earth. The universe operates on timescales that dwarf human experience, and there's something oddly comforting about that vastness. Yet the dream of faster-than-light travel persists, and not just in science fiction. Serious researchers continue to study the theoretical possibilities, publishing papers and exploring equations that might reveal loopholes in the apparent speed limit. Part of this persistence comes from human nature itself. We've always pushed boundaries that once seemed absolute. Flight was impossible until it wasn't. Space travel was fantasy until it became routine. Landing on other worlds seemed absurd until humans actually did it. The study of faster-than-light possibilities also touches something deeper than engineering or transportation. It probes the fundamental structure of reality itself. When physicists explore these concepts, they're really asking questions about the nature of space, time, causality, and information. These aren't just technical problems, they're philosophical puzzles about how existence itself is organized. Some proposed faster-than-light mechanisms involve exotic forms of matter that may not even exist. Others require energy levels that dwarf anything humanity could currently generate. Still others depend on spatial geometry so strange they're difficult to visualize. Wormholes, for instance, would theoretically connect distant regions of space through shortcuts that bypass normal three-dimensional geometry entirely. The mathematics behind these ideas often works beautifully on paper, even when the practical challenges seem insurmountable. This creates a fascinating tension between what the equations allow and what reality might actually permit. Scientists must navigate carefully between theoretical possibility and physical feasibility, always aware that the universe often surprises us with behaviors we didn't expect. Perhaps the most intriguing aspect of faster-than-light research is how it forces us to question assumptions we rarely examine. We assume space and time are smooth, continuous, unchanging backgrounds against which events unfold. But what if space-time itself can be engineered, manipulated, folded like origami? What if the apparent solidity of physical law is more flexible than it appears? These questions remain largely unanswered, suspended between imagination and rigorous scientific inquiry. The universe keeps its secrets well, revealing them slowly through careful observation and mathematical analysis. Whether faster-than-light travel will ever become reality remains one of the great open questions of our time, a puzzle that continues to challenge our understanding of what's possible in this strange and wonderful cosmos we inhabit. Standing on a quiet road, watching a car pass by, you can judge its speed with ease. The faster it moves, the more the scenery blurs. When it slows down, your eyes can follow it smoothly. This everyday experience makes speed seem straightforward, almost trivial. Distance divided by time, nothing more complicated than that. For centuries, scientists believed all motion worked exactly this way. If you threw a ball forward from a moving ship, they thought its speed relative to the shore would simply be the ship's speed plus your throwing speed. Everything would add together like numbers on paper. Light, they assumed, should behave identically. Picture yourself holding a lantern on a moving carriage. According to this old thinking, the light should travel faster in the direction of motion, slower in the opposite direction. This logic matched everything people knew about moving objects. It felt perfectly reasonable, and no one questioned it for a very long time. But the universe, as it often does, had prepared a surprise that would change everything we thought we knew. During the 19th century, scientists began measuring light speed with remarkable precision. Their experiments grew more careful, their instruments more refined. Slowly, something extraordinary emerged from these measurements. No matter how fast a light source was moving, The measured speed of light stayed exactly the same. It made no difference whether light came from a lamp, sitting on a table, or from a distant star, racing through space. The light always arrived at precisely the same speed. This was deeply puzzling, like discovering that a ball thrown from a speeding train always traveled at the same speed relative to the ground, regardless of the train's velocity. Such behavior shouldn't happen, not according to the physics people understood then. To explain this mystery, scientists proposed something called the luminiferous ether. They imagined this as an invisible substance filling all of space, a kind of cosmic medium through which light waves moved. Think of it as a silent ocean permeating everything. If Earth traveled through this ether, scientists reasoned, light speed should appear slightly different depending on which direction you measured it. Just like swimming upstream feels different from swimming downstream. So they designed experiments to detect this effect. The most famous experiment happened in 1887. Albert Michelson and Edward Morley created an apparatus so sensitive it could detect incredibly tiny differences in light speed. If Earth were truly moving through an ether, their experiment should have revealed it without question. But it didn't. No matter how carefully they measured, no matter how they positioned their equipment, light speed remained stubbornly unchanged. The ether, it seemed, simply wasn't there. This result made scientists deeply uncomfortable. It contradicted the basic assumptions of classical physics. Various explanations emerged. Some suggested that objects physically contracted when moving. Others proposed subtle adjustments to existing theories. But none of these explanations felt entirely satisfying. They seemed like patches rather than genuine understanding. Then, in 1905, Albert Einstein offered something completely different. Instead of trying to explain why light speed appeared constant, he proposed that it truly was constant. The laws of physics themselves, he suggested, ensured this constancy. For this to work, something much more fundamental had to change. Space and time, Einstein realized, could not be fixed and absolute. They had to be flexible, able to adjust themselves to keep light speed the same for all observers. This idea became known as special relativity. At first glance, it seems almost impossible to accept. We're accustomed to thinking of time as flowing steadily, the same for everyone, everywhere. We imagine lengths and distances as solid, unchanging measurements. But relativity reveals that both time and space can shift depending on how fast you're moving. Time can slow down for someone traveling at high speeds. Lengths can contract in the direction of motion. Even the order of events can depend on who's observing them. All these strange effects arise from one simple principle. Nothing can carry information faster than light travels. This gives the universe its ultimate speed limit, a boundary that nothing can cross. But why should such a limit exist at all? Why would nature impose a maximum speed on anything? One way to understand this is by imagining cause and effect as ripples spreading through a pond. When you drop a pebble into still water, ripples move outward at a speed determined by the water's properties. No signal can travel faster than those ripples because the ripples themselves are the mechanism by which disturbances spread. The water can't communicate changes to itself any faster than its own physical properties allow. Space operates similarly. Light represents the fastest way that changes can spread through the fabric of space and time. It's not just light rays that obey this limit. Gravity waves, electromagnetic signals, any form of information, all follow the same restriction. This isn't a limitation imposed by poor engineering or inadequate materials. It's not something we might overcome with better technology or clever design. Instead, it's a fundamental feature of space-time structure itself. The universe has built this speed limit into its most basic architecture. Think about what this means. Every cause must wait for its effect. Every signal must travel at finite speed. Every change must propagate through space one step at a time. In a strange way, this limitation creates the very possibility of sequence, of before and after, of the ordered flow of events we call time. Without this cosmic speed limit, cause and effect might become meaningless concepts. Events could influence their own past. The careful chain of causality that makes the universe comprehensible would dissolve into chaos. Perhaps the speed limit isn't really a restriction at all. Maybe it's more like the rules of grammar that make language possible, or the laws of harmony that make music beautiful. Sometimes boundaries don't limit us. They create the very framework within which meaning can exist. The universe operates on a foundation of cause and effect, where one thing leads to another in a predictable sequence. This might seem obvious, but it's actually one of the most profound organizing principles of reality. When we send a signal or create an event, that information spreads outward at a specific rate, never faster than the speed of light. This creates a natural order, where causes always come before their effects, at least from any single observer's perspective. But imagine if we could somehow break this rule. If we could send information faster than light, something truly bizarre would happen. According to the mathematics of relativity, that signal could actually arrive before it was sent, at least from the viewpoint of certain observers moving at high speeds. The universe would suddenly become a place where replies arrive before questions, where effects happen before their causes. Reality itself would become contradictory, tangled in impossible loops. This isn't just a mathematical curiosity. The speed of light acts as a cosmic referee, maintaining the logical structure of existence. It ensures that information cannot leap ahead of its origins, preserving the sequence that makes the universe comprehensible. Without this boundary, the very notion of causality would crumble, and with it, our ability to make sense of anything at all. The speed limit doesn't make the universe static, though. Space itself can stretch and expand, carrying galaxies apart faster than light, but this is different from objects moving through space. When space expands, it's like dots on a balloon growing farther apart as the balloon inflates. The dots themselves aren't moving faster than light. The balloon is simply getting bigger. In any local region, however, objects with mass face an insurmountable barrier. That barrier reveals itself through energy. As any object accelerates, the energy required to push it faster grows larger and larger. At everyday speeds, this increase is barely noticeable. A car going 60 miles per hour doesn't need dramatically more energy than one going 50, but as speeds approach that of light, something remarkable happens. The energy requirements don't just grow, they explode toward infinity. Infinity in physics is usually nature's way of saying something is impossible. It's like trying to climb an increasingly steep hill that eventually becomes a sheer cliff. No matter how much effort you apply, you simply cannot reach the top, because the path itself prevents it. This is why particles with mass can never quite reach light speed, no matter how much energy we throw at them. The most powerful particle accelerators on Earth demonstrate this limit beautifully. These machines use tremendous energies to push tiny particles to incredible velocities, bringing them tantalizingly close to the speed of light, but they can only approach it, never actually reach it. The particles get closer and closer, like an asymptotic curve that forever approaches but never touches a line. Only particles without mass, like photons, naturally travel at light speed. They don't accelerate to this velocity, they simply exist at it. Mass, in a sense, is what prevents other particles from joining them at this cosmic speed limit. It's as if mass creates a drag that becomes infinite as you approach the boundary of space-time. Yet the story becomes more intriguing when we consider the geometry of space itself. While objects cannot exceed light speed by moving through space, the structure of space might offer other possibilities. Einstein's equations describe how massive objects warp space-time, curving it like a heavy ball placed on a stretched rubber sheet. This curvature doesn't just affect how objects move, it affects the very meaning of distance. Consider a simple analogy. If you want to travel between two distant points on a flat piece of paper, you normally walk across the surface, but if you could fold that paper so the 2 points touched, you could step from one to the other instantly. You haven't moved faster than your normal walking speed, you've simply changed the geometry of your journey. This geometric insight has inspired concepts like warp drives and wormholes. These theoretical constructs don't require objects to exceed light speed locally. Instead, they imagine reshaping space itself, contracting the distance ahead and expanding it behind, or creating tunnels that connect distant regions of the universe. The object never breaks the speed limit in its immediate vicinity, but it might traverse vast distances by taking shortcuts through the fabric of space-time. Whether such things could actually exist remains an open question. The mathematics allows for them, but mathematics often permits things that nature forbids. Building a warp drive might require exotic forms of matter with negative energy density, substances that may not exist or may be impossible to control. Wormholes might collapse the instant anything tries to pass through them, or they might require the same exotic matter to remain stable. Scientists approach these possibilities with careful skepticism, treating them as fascinating thought experiments rather than engineering blueprints. The universe has shown us repeatedly that just because something is mathematically possible doesn't mean it's physically achievable. Nature seems to have her own preferences about what she allows. There's something deeply satisfying about the existence of this cosmic speed limit. The universe has a rhythm, a fundamental pace at which events can unfold and information can travel. This isn't chaos or randomness, it's structure. It's a reliable, consistent framework that governs everything from the smallest quantum interactions to the largest cosmic events. In a sense, the speed of light gives time its meaning. Without this boundary, simultaneity would lose all definition. Causality would become meaningless, and the universe would collapse into logical contradiction. Instead, we inhabit a cosmos with rules, limits, and boundaries that create the very possibility of order and understanding. Perhaps there's something philosophical to contemplate in this universal speed limit. It reminds us that even in a universe of incredible vastness and complexity, there are fundamental constraints that shape reality. Not everything is possible, and sometimes the impossible barriers are exactly what make existence meaningful and comprehensible. The speed of light stands as one of the universe's most fundamental constants, traveling at exactly 299,792,458 meters per second through the vacuum of space. This number remains the same, regardless of where you measure it, or how fast you happen to be moving when you take the measurement. But what does this actually mean when we try to picture it in our minds? Large numbers like 300,000 kilometers per second tend to wash over us without leaving much of an impression. Our brains recognize that the figure sounds impressive, then quietly move on to something easier to grasp. The human mind evolved to understand the speed of a running animal, or the flow of a river, not cosmic velocities that dwarf everything in our daily experience. Let's start with something familiar, our own planet. Earth measures about 40,000 kilometers around its equator, a distance that would take months to walk. Light could race around this entire circumference more than 7 times in just 1 second. Imagine watching a beam of light zip around the globe again, and again, and again, all before you could even finish pronouncing the word second. Turn on a flashlight in your bedroom tonight, and the light seems to reach the walls instantly. Even in a massive sports stadium, light arrives at the far end so quickly that no human sense can detect the delay. For most of our species' history, people naturally assumed that light traveled instantaneously. This assumption made perfect sense, because on human scales, light essentially does arrive instantly. The illusion breaks down only when distances grow large enough for even light to take noticeable time. Our moon sits about 380,000 kilometers away, far enough that light needs just over 1 second to make the journey. When Apollo astronauts spoke to mission control from the lunar surface, their voices traveled as radio waves at light speed, creating a subtle but noticeable pause in every conversation. You can still hear this rhythm in old recordings, a gentle back and forth that reflects the finite speed of information itself. Sunlight takes roughly 8 minutes to reach Earth. This means that when you step outside and feel warmth on your face, you're experiencing light that began its journey 8 minutes ago. If our sun were to suddenly vanish, which thankfully shows no signs of happening, Earth would continue receiving light and heat for those 8 minutes before anything changed. We would keep orbiting a star that no longer existed, living for a brief moment on borrowed time. The nearest star system beyond our own, Proxima Centauri, lies about 4.2 light-years away. A light-year represents the distance that light travels in an entire year, roughly 9.5 trillion kilometers. When you look up at Proxima Centauri on a clear night, the light entering your eyes began its journey more than 4 years ago. You're seeing that star as it existed when your life looked quite different, perhaps in a different season, with different concerns, different plans, different dreams. This reveals one of astronomy's most profound truths. Looking into space means looking into the past. The deeper we peer into the cosmos, the further back in time we see. Every telescope becomes a time machine, showing us not what distant objects look like now, but what they looked like when their light began traveling toward us. These time delays help explain why faster-than-light travel captures our imagination so powerfully. Even traveling at light speed, a journey to Proxima Centauri would take more than 4 years. Crossing our entire Milky Way galaxy would require about 100,000 years, longer than human civilization has kept written records. When science fiction shows spacecraft hopping between star systems in hours or days, it's not just taking small liberties with physics, it's leaping across an enormous chasm between what the universe allows and what makes for exciting storytelling. To really grasp light speed, it helps to compare it with velocities we know. A commercial airliner cruises at about 900 kilometers per hour. High-speed trains might reach 300 kilometers per hour. Cars on highways typically move at 100 kilometers per hour. Even the fastest military jets, flying at several times the speed of sound, achieve only a few thousand kilometers per hour. Compared to light, all these speeds are practically motionless. Imagine organizing a race between a beam of light and the fastest jet aircraft, both traveling around Earth's equator. The light would complete more than 7 full laps in the time the aircraft covered just 1 kilometer. The difference isn't just dramatic, it's almost incomprehensible. Even our most advanced spacecraft barely register on this scale. NASA's Parker Solar Probe, one of the fastest human-made objects ever built, reaches speeds of around 700 kilometers per hour when it swings close to the Sun. This represents an extraordinary achievement of engineering and physics. Yet light still travels more than 400 times faster. Try imagining light speed scaled down to something familiar. If light moved at the speed of a car, driving 100 kilometers per hour, then on that same scale, our fastest spacecraft would crawl forward at only a few centimeters per hour, slower than grass growing, slower than paint drying, barely faster than geological processes. This scaling reveals the true challenge of interstellar travel. Space isn't just big, it's vast beyond everyday comparison. Even signals moving at the ultimate speed limit face significant delays when distances grow large enough. Communication with Mars missions takes anywhere from 4 to 20 minutes each way, depending on where both planets happen to be in their orbits around the Sun. Engineers operating rovers on Mars cannot steer them in real time like remote control cars. Every command must be sent across millions of kilometers. Then operators must wait patiently for responses, knowing their instructions travel at the fastest speed the universe permits. This delay fundamentally shapes how missions are designed. Rovers need built-in intelligence to navigate obstacles and make basic decisions independently. Mission plans must be crafted carefully in advance, with no possibility of instant corrections. Journey to the outer planets, and these delays grow even longer. Signals to Jupiter require about 40 minutes for a round trip. Messages to Saturn can take more than 2 hours. At the edge of our solar system, where the Voyager probes now travel through interstellar space, communications take well over a day to arrive and return. These timescales remind us that even light speed, remarkable as it is, doesn't erase distance. It only makes the vastness manageable enough for patient exploration. Understanding light speed also opens a window into one of the universe's stranger properties. At the low speeds we experience in daily life, time behaves exactly as our intuition expects. Seconds tick by at the same rate for everyone nearby. Clocks agree with each other. Motion doesn't noticeably affect the flow of time itself, but as speeds increase toward light speed, time begins to behave differently. This effect, called time dilation, means that a clock moving very fast will tick more slowly compared to one at rest. At airplane speeds, the difference is incredibly tiny, measurable only with atomic clocks and detectable only as fractions of microseconds. Still, the effect is real and has been confirmed through precise experiments. The principle becomes dramatic as speeds approach light speed. If a spacecraft could somehow travel at 99% of light speed, time for the travelers would pass more slowly than for people remaining on Earth. A journey that felt like a few years to those aboard might correspond to decades passing for friends and family at home. This is one reason why relativistic travel, even without exceeding light speed, leads to consequences that challenge our intuitive understanding of time and aging. Interestingly, nothing with mass has ever been observed actually reaching light speed. Particle accelerators can push subatomic particles to more than 99.9% of light speed, but never quite to the limit itself. Each additional fraction of speed requires more energy than the previous fraction, as if the universe quietly resists these attempts. It's not a sharp barrier or sudden wall, but more like climbing a slope that becomes steeper and steeper until further progress demands more energy than any conceivable machine could provide. This helps explain why faster-than-light travel remains such a challenging problem. Light speed isn't just another velocity limit, like a highway speed limit, that you might exceed with a more powerful engine. It's woven into the fundamental structure of space and time itself. It defines how quickly cause can lead to effect, how fast information can travel, how distant parts of the universe remain connected to each other. Yet, despite all these constraints, physicists continue exploring possibilities. Because while nothing with mass can accelerate past light speed through space, the geometry of space itself proves more flexible than it first appears. Einstein's general relativity describes space not as a rigid, unchanging stage, but as something that can bend, stretch, and curve under the right conditions. Under certain circumstances, distances might change in ways that resemble shortcuts. Paths where the effective journey becomes shorter without violating the local speed limit. These concepts remain largely theoretical, and many involve conditions far beyond anything we can currently create or control, but they demonstrate that the question of faster-than-light travel isn't entirely closed. These ideas exist in that fascinating territory where physics sets firm rules, yet still leaves room for curiosity and wonder. Perhaps that's fitting for a universe that allows light to travel fast enough to circle our entire planet 7 times in a single second, yet still takes years to carry messages between neighboring stars. Light moves at the same speed whether it comes from the sun, or carries a radio signal, or transmits an image across continents. This one fundamental pace connects everything, carries all information, and sets the rhythm for the entire cosmos. It's a universal constant that touches every corner of existence. By the early 1900s, scientists were starting to notice cracks in their understanding. Measurements weren't matching what they expected anymore. The laws that had worked perfectly for centuries were showing small, persistent problems, like hairline fractures appearing in otherwise solid glass. Newton's laws of motion were still incredibly useful for everyday life, but there were growing hints that the complete story was much more complex. Einstein wasn't working in some grand laboratory when he began thinking about these problems. He was a young patent clerk, doing his thinking quietly, in spare moments. He loved what he called thought experiments, where he would imagine scenarios in his mind and follow them, step by step, asking what physics would allow and what it would forbid. One question fascinated him above all others. What would it look like to ride alongside a beam of light? It sounds almost playful, the kind of thing you might wonder about while watching sunlight stream through a window. But when Einstein examined this question carefully, he realized it led to a serious contradiction. According to the physics of his time, if you moved fast enough to keep pace with a light wave, you should see that wave frozen in space, like a ripple in water that had stopped moving. But no one had ever observed such a thing. The equations of electromagnetism suggested it simply couldn't happen. Light always moved at the same speed, no matter how fast the observer was traveling. This realization became the foundation for special relativity, published in 1905. The theory rests on two principles that sound simple when you state them plainly. First, the laws of physics are the same for all observers moving at constant speeds relative to one another. Second, the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the source. At first glance, these ideas don't seem especially radical, but when you follow them to their logical conclusions, they reveal a universe that behaves very differently from what common sense suggests. Consider this scenario. Two observers, one standing on a platform, the other riding on a train, moving at very high speed. A flash of light occurs inside the train, halfway between the front and the back. To the passenger inside, the light reaches both ends at exactly the same time. That seems obvious, since the flash started in the middle and light travels equally in all directions. But to the observer on the platform, the situation looks completely different. From that perspective, the back of the train is moving toward the place where the flash occurred, while the front is moving away from it. Since the speed of light must be the same in all directions, the light reaches the back of the train before it reaches the front. Two observers, both correct in their own frames of reference, disagree about whether the two events happened at the same time. This is what physicists call the relativity of simultaneity. It was one of the first signs that time itself is not absolute. Events that appear simultaneous to one observer may not be simultaneous to another. Once you accept that idea, other consequences follow naturally. Time doesn't pass at the same rate for everyone. A clock moving at high speed ticks more slowly than one at rest. This isn't a flaw in the clock or a trick of measurement. It's a real physical effect that has been confirmed by countless experiments. Particles moving near the speed of light actually live longer than they would at rest. Atomic clocks flown on aircraft and satellites run at slightly different rates than those on the ground. Time dilation isn't science fiction, it's a measurable fact of nature. There's something profound about realizing that time itself is flexible, that the steady tick we take for granted can stretch and compress depending on motion. Length change too. Objects moving at high speed appear shortened in the direction of motion, an effect known as length contraction. Again, this isn't an illusion, but a consequence of the way space and time are linked together. The very fabric of reality responds to motion in ways that challenge our everyday understanding. Energy behaves differently as well. As an object moves faster, its kinetic energy increases, but not in the simple way Newton's equations predict. Near the speed of light, the energy required to accelerate further grows dramatically. Pushing an object with mass to light speed would require an infinite amount of energy. That requirement forms one of the most fundamental barriers in physics. It's not a wall you can crash into, nor a force field that stops you suddenly. It's more like an asymptote, a limit that can be approached but never reached. No matter how much energy you add, the speed gets closer and closer to light speed, but the final step remains forever out of reach. This is why the speed of light is often described, not just as a speed, but as a cosmic speed at which matter, energy, and information can travel through space. So far, no experiment, no observation, and no particle accelerator has ever broken that limit. It has been tested again and again, in laboratories and in space, under conditions far more extreme than anything encountered in daily life. Every result confirms the same conclusion. The laws of relativity hold true. The speed of light remains constant. The barrier stands firm. There's something quietly remarkable about that consistency, about finding a rule that seems to govern everything in the universe without exception. It suggests a deep order underlying the apparent chaos of existence, a fundamental structure that connects the smallest particles to the largest galaxies. Physics has this peculiar way of showing us that the universe operates by rules we never expected. Take the speed of light, for instance. It's not just fast, it's the ultimate speed limit, built right into the fabric of reality itself. Every photon that traveled across the cosmos billions of years ago followed exactly the same rules as the light coming from your phone screen right now. There's something almost comforting about that consistency, even if we don't fully grasp why it has to be that way. Einstein figured this out over a century ago with his special theory of relativity, but he didn't stop there. A decade later, he completely revolutionized how we think about gravity itself. In his new picture, gravity wasn't some invisible force yanking things together, like Newton thought. Instead, massive objects actually warp the geometry of space and time around them. Think of it like dropping a bowling ball onto a trampoline. The fabric dips, and if you roll marbles nearby, they naturally curve toward the bowling ball, not because they're being pulled, but because the surface itself is bent. This idea merged space and time into something called space-time, a single four-dimensional structure that can stretch, compress, and curve. And here's where things get really strange. Time itself can slow down in stronger gravitational fields. This isn't science fiction, it's measurable reality. The clocks on GPS satellites actually run faster than clocks on Earth's surface because they're farther from our planet's gravitational well. Without accounting for this time dilation, your navigation system would be off by several kilometers every single day. So relativity isn't just some abstract theory sitting in textbooks. It's quietly working in the background of technologies we use constantly, making sure your maps actually show you where you are. But the implications go far beyond getting to the grocery store on time. These same principles govern black holes, the expansion of the entire universe, and why faster-than-light travel seems so impossibly difficult. The speed limit isn't just about building a more powerful rocket engine. It's woven into the very structure of space-time itself. To exceed the speed of light would mean breaking the relationships that keep cause and effect in proper order throughout the universe. Imagine trying to arrive somewhere before you actually left. The mathematics of relativity suggests this would create paradoxes that reality simply doesn't allow. Yet, even as relativity imposes this cosmic speed limit, it also hints at stranger possibilities. The equations of general relativity allow for some truly bizarre solutions. Wormholes, for example, could theoretically exist as bridges connecting distant parts of space. Scientists have even proposed warp drive concepts that would contract space in front of a spacecraft while expanding it behind, allowing faster-than-light travel without technically breaking the local speed limit. These ideas remain highly speculative, and most require exotic forms of matter or energy that probably don't exist. But their presence in the equations shows us that the universe might be more subtle than we initially thought. It's not just a simple rulebook of what's forbidden and what's allowed. For now, though, that barrier remains completely unbroken. Every particle accelerator, every astronomical observation, every precise measurement confirms the same thing. Nothing with mass can reach light speed, and nothing has ever been observed exceeding it. There's something almost humbling about this fact. Human technology has advanced at an incredible rate over the past century. We've walked on other worlds, sent spacecraft to the edge of the solar system, built instruments sensitive enough to detect ripples in space-time itself. And yet this speed limit, discovered more than 100 years ago, stands as firm as ever. It reminds us that the universe isn't obligated to bend to our ambitions. Some boundaries aren't temporary engineering problems, waiting to be solved. They're reflections of deeper principles that govern how reality actually works. But understanding these principles often opens up entirely new ways of thinking. Once upon a time, the idea that time could slow down or that space could curve seemed completely absurd. Now they're established scientific facts, so while the speed of light remains our cosmic speed limit, the study of relativity keeps revealing new insights about the fundamental nature of reality. And that leads to an intriguing question. If nothing can move through space faster than light, perhaps space itself could be shaped or manipulated in ways that make distant journeys take less time than they normally would. It's a thought that continues to fascinate both physicists and dreamers, pushing us to imagine possibilities we haven't yet discovered. The universe holds a secret that becomes visible only when things move extremely fast. Most of the time, we never encounter this hidden reality. Our cars, our planes, Even our fastest rockets all move at speeds that are laughably slow compared to light. At these everyday velocities, the world behaves exactly as we expect it to. Clocks tick at their normal pace, rulers measure distances the same way they always have, and time flows uniformly for everyone. But nature has been keeping something from us. As objects begin to approach truly high speeds, reality itself starts to shift in ways that challenge everything we think we know about time and space. These changes don't happen all at once, like crossing some invisible line. Instead, they creep in gradually, becoming more pronounced as speeds climb higher and higher. Think about cosmic rays, those high-energy particles that constantly bombard our planet from deep space. When these rays collide with molecules in the upper atmosphere, they create new particles called muons. Now, muons have a problem. They're incredibly short-lived. Under normal circumstances, they would decay and disappear long before they could travel the 100 kilometers or so down to Earth's surface. Yet somehow, we detect vast numbers of them in laboratories around the world. The explanation lies in one of the most profound discoveries in physics: time dilation. When muons race through the atmosphere at speeds approaching that of light, time itself slows down for them. From our perspective on the ground, their internal clocks are running in slow motion. What feels like a brief moment to us gives them enough time to complete their journey before they decay. But here's where it gets really interesting. From the muons' point of view, something entirely different is happening. To them, time passes normally, but the distance they need to travel shrinks. The thick blanket of atmosphere that should take too long to cross becomes compressed, contracted in the direction of their motion. Both explanations are correct, depending on where you're standing when you observe the phenomenon. This isn't just theoretical physics, it's measurable reality. Atomic clocks, those incredibly precise timekeeping devices, actually run at different rates depending on how fast they're moving. When scientists fly identical atomic clocks on high-speed aircraft, they tick at slightly different rates than the ones left on the ground. The differences are tiny, measured in billionths of a second, but they're real and consistent. GPS satellites experience this effect every day. They orbit Earth at high speeds, and their onboard clocks run slightly faster than clocks on the surface. If engineers didn't account for this time difference, GPS coordinates would drift by several kilometers each day. Your phone's ability to pinpoint your location depends on understanding how time behaves at high speeds. As velocities increase even further, these effects become dramatic. Imagine a spacecraft traveling at 99% the speed of light. The people aboard would experience time passing normally. Their heartbeats, their breathing, their thoughts would all proceed at the familiar pace. But to observers on Earth, everything on that ship would appear to be moving in extreme slow motion. A journey that feels like a few years to the travelers might correspond to decades passing back home. This leads to one of the most haunting scenarios in physics, sometimes called the twin paradox. One twin stays on Earth, while the other embarks on a high-speed journey through space. When the traveling twin returns, they find themselves younger than their sibling, who remained behind. It's not magic, it's the fundamental nature of time itself. We're accustomed to thinking of time as universal, flowing at the same rate everywhere in the universe. But relativity reveals that time is more like a river with varying currents. Your motion through space determines how quickly you move through time. The faster you travel through space, the slower you travel through time, and vice versa. Space itself behaves just as strangely. Objects moving at very high speeds appear to contract, becoming shorter in the direction of their motion. A spacecraft racing toward you at nearly light speed would look compressed, as if someone had squeezed it, like an accordion. Yet the people inside would notice nothing unusual about their ship's dimensions. This contraction of space provides another way to understand the muon mystery. From the muon's perspective, it's not that time is slowing down, it's that the atmosphere is getting thinner, compressed in the direction of travel. The distance to the ground shrinks, allowing the muon to complete its journey before decay. Time dilation and length contraction are really two aspects of the same phenomenon. They're different ways of describing how the geometry of space-time itself responds to high-speed motion. These effects reveal that space and time aren't separate, independent things, but parts of a unified structure that can stretch and compress. Other strange effects emerge at extreme speeds. Light itself begins to behave differently. We're familiar with how the pitch of an ambulance siren changes as it approaches, and then recedes. Light undergoes a similar shift, but at high speeds, this Doppler effect becomes extreme. If you were somehow traveling toward a star at a significant fraction of light speed, the star's light would shift toward higher frequencies. Red light would appear blue, blue would shift into ultraviolet, and eventually into X-rays and gamma rays. The gentle starlight that seems so peaceful from Earth would become a beam of deadly radiation. Looking backward during such a journey, the opposite would occur. The light from stars behind you would shift toward lower frequencies, moving from visible light into infrared and then radio waves, essentially becoming invisible. The universe ahead would glow with dangerous energy while the cosmos behind would fade into darkness. The very directions of starlight would appear to change. Light that normally arrives from all directions would seem to crowd toward the front of your spacecraft, concentrating into a brilliant cone ahead while the sky behind darkens. The familiar constellations would distort beyond recognition. The peaceful dome of stars we see from Earth would become an alien landscape of concentrated radiation and empty darkness. These effects raise profound questions about the nature of perception itself. What we consider the real appearance of the universe depends entirely on our state of motion. There's no single, correct view of reality, only different perspectives that reveal different aspects of the same underlying truth. The energy requirements for such journeys present their own philosophical puzzles. As an object accelerates closer and closer to light speed, each additional increment of velocity requires more energy than the last. The relationship isn't linear, it's exponential. Getting from 90% to 95% light speed takes vastly more energy than getting from 50% to 90%. Near light speed, the energy requirements grow so dramatically that they approach infinity. This isn't a limitation of our technology or our fuel sources, it's a fundamental feature of reality itself. The universe seems to have built-in protections against exceeding the speed of light, making it not just difficult, but mathematically impossible for anything with mass to reach that ultimate velocity. Even approaching light speed would demand resources on a scale that's difficult to imagine. The fuel requirement alone might exceed the mass of entire planets. The heat generated would be enormous, requiring cooling systems beyond anything we've ever built. The spacecraft itself would need to be engineered to withstand forces and stresses unlike anything experienced on Earth. There's also the matter of interstellar debris. Space, though often described as empty, contains tiny particles of dust and gas scattered throughout. At ordinary speeds, these particles pose no threat. They're too small and too dispersed to matter. But at a significant fraction of light speed, even a microscopic grain of sand becomes a devastating projectile. The kinetic energy of a dust particle striking a spacecraft at 90% light speed would be equivalent to a powerful explosive. Protecting against such impacts would require shielding far beyond anything currently possible, or perhaps entirely new technologies for detecting and deflecting particles before collision. All of these challenges paint a picture of near light speed travel that's both magnificent and terrifying. The physics allows it in principle. The equations of relativity don't forbid such journeys, but the practical difficulties are staggering, and the consequences for human experience would be profound. Yet, there's something deeply compelling about the possibility. Such a journey would be more than just travel through space. It would be travel through time itself. A crew departing Earth might return to find that centuries had passed, that civilizations had risen and fallen, that the world they remembered existed only in history books. This raises questions that extend far beyond engineering and physics. What would it feel like to leave behind everyone you've ever known, understanding that even if you returned, they would be long gone? How would the human mind cope with the knowledge that each moment of your journey corresponds to days or weeks passing in the world you left behind? These are the kinds of questions that belong as much to philosophy as to science. They force us to confront fundamental assumptions about identity, continuity, and what it means to be human in a universe where time itself can stretch and compress. The cosmic speed limit remains unbroken, standing as one of the universe's most fundamental laws. Even these extreme journeys, extraordinary as they would be, cannot actually reach light speed itself. That barrier appears to be absolute, built into the very fabric of reality, ensuring that some boundaries can never be crossed, no matter how advanced our technology becomes. The speed of light stands like an immovable wall in physics, refusing to bend to human ambition. For decades, scientists threw themselves against this barrier, trying to push spacecraft faster and faster still. But eventually, a different thought emerged. What if the journey itself could become shorter? What if space, the very stage where everything happens, could be manipulated? Picture yourself walking across a vast field on a quiet afternoon. The obvious way to reach the other side faster is to quicken your pace. But imagine if the field could suddenly shrink beneath your feet, or if a hidden path appeared, cutting straight through. You'd arrive sooner without ever walking faster. Your personal speed limit would stay exactly the same, yet time would compress around you. This simple idea captures something profound about our universe. Space isn't the rigid, unchanging backdrop we experience in daily life. According to Einstein's theory of general relativity, space and time weave together into a fabric, one that bends and flexes under the influence of mass and energy. Stars warp this fabric around themselves. Planets create gentle curves in space-time. These distortions aren't just mathematical curiosities, they shape how everything moves. The evidence surrounds us, quietly confirming these strange truths. Light from distant stars bends slightly as it passes near our sun, following the curved geometry that gravity creates. Atomic clocks tick at different rates depending on how high above Earth's surface they sit. Mercury's orbit shifts in ways that Newton's laws alone cannot explain, but Einstein's equations predict with perfect precision. So space can bend, that much we know. The deeper question becomes whether it can bend enough, in just the right way, to allow something resembling faster than light travel without actually breaking the cosmic speed limit. The universe itself offers a tantalizing hint. Distant galaxies rush away from us, and the farther they are, the faster they recede. At enormous distances, this expansion carries galaxies away, faster than light itself. This might sound like a violation of relativity, but it's actually perfectly allowed. Those galaxies aren't racing through space faster than light. Instead, the space between us and them is expanding. Nothing locally exceeds light speed, but globally, distances grow faster than light could cross them. This distinction matters enormously. The speed limit applies to motion through space, not necessarily to changes in space itself. Once physicists grasped this subtle difference, they began exploring theoretical solutions that involve unusual distortions of space-time. Some of these solutions describe regions where space contracts in one direction while expanding in another, effectively carrying objects along without requiring extreme local speeds. The most famous of these ideas is the warp drive concept. The principle sounds almost simple, though the practice would be extraordinarily complex. Instead of accelerating a spacecraft through space, a warp drive would create a bubble of space-time around the vessel. Space in front of the bubble would contract, while space behind it would expand. The craft itself would remain perfectly still within this bubble, never locally exceeding light speed, yet the bubble could move faster than light relative to distant observers. Think of those moving walkways at airports. You can stand completely motionless on the walkway while it carries you forward. Your speed relative to the walkway is 0, but your speed relative to the terminal building is much greater. In a warp drive scenario, the walkway would be space-time itself, flowing around your vessel like a cosmic river. In 1994, physicist Miguel Alcubierre found a mathematical solution to Einstein's equations describing such a warp bubble. The solution showed that, at least on paper, faster than light travel might be possible without violating relativity. But there was a significant catch. Creating the required curvature of spacetime demanded a form of matter with negative energy density, sometimes called exotic matter. This isn't something we encounter in everyday life. All familiar matter, from rocks to stars to the air we breathe, has positive energy density. Exotic matter, if it exists at all, would behave in very unusual ways. Quantum physics provides small hints that negative energy densities can occur under certain conditions. The Casimir effect, for instance, causes closely spaced metal plates to experience a tiny attractive force due to quantum fluctuations. But these effects are extremely small, far from what would be needed to power a warp drive. Early estimates suggested the amount of negative energy required might equal the mass energy of an entire planet, or even a star. Later refinements reduced the estimate somewhat, but it remains far beyond anything humanity could produce. Energy isn't the only challenge either. Even if a warp bubble could be created, controlling it would present enormous difficulties. Some calculations suggest that information cannot be transmitted from inside the bubble to its front edge. The occupants might not be able to steer or stop once the bubble formed. Other studies indicate that harmful radiation could build up at the front of the bubble and be released in a dangerous burst when the bubble stopped. These issues don't necessarily prove that warp drives are impossible, but they reveal how complex the problem truly is. Another approach involves wormholes, hypothetical tunnels connecting distant points in space-time. If such a tunnel existed, traveling through it could allow a journey of thousands of light years to be completed in much shorter time, because the path through the wormhole would be shorter than the path through normal space. Imagine drawing two dots on a sheet of paper. The straight line distance between them might be quite long, but if you fold the paper so the dots touch, you can move from one to the other instantly. The folding represents a shortcut through higher dimensional geometry. Wormholes appear in certain solutions of general relativity, and the mathematics describing them is well understood, but like warp drives, they seem to require exotic matter to remain stable. Without such matter, a wormhole would collapse too quickly for anything to pass through. There's also the unanswered question of whether wormholes could form naturally. Some theories suggest they might arise in extreme conditions, perhaps in the early universe or near black holes, but no observational evidence has confirmed their existence. Even if wormholes do exist, finding one, reaching it, and stabilizing it would present challenges far beyond our current capabilities. Still, the fact that these ideas emerge naturally from the equations of relativity is remarkable. It shows that the universe allows possibilities far stranger than the everyday world suggests. At the same time, physicists approach these concepts with appropriate caution. Mathematics can describe many things that don't exist in reality. The equations of fluid dynamics, for example, allow perfectly smooth flows that never become turbulent. Yet real fluids almost always develop turbulence under the right conditions. Nature has a way of imposing additional constraints that equations alone don't reveal. There's also the question of energy on a cosmic scale. Bending spacetime significantly requires enormous amounts of energy, because spacetime isn't easily reshaped. Gravity, though it feels weak in everyday life, governs the motion of stars and galaxies. Altering spacetime enough to create a warp bubble or stable wormhole would involve energies comparable to those found in astrophysical events. Another challenge is stability. Even small disturbances in the geometry of spacetime can grow rapidly under certain conditions. A warp bubble or wormhole might require constant adjustments to remain intact, much like balancing a pencil on its tip requires continuous corrections. Despite these obstacles, research continues. Physicists explore theoretical models, refine calculations, and look for ways to reduce energy requirements or identify new physical effects that might make such technologies more feasible. There's growing interest in analog systems, laboratory experiments that mimic certain aspects of spacetime behavior, using fluids, optical materials, or other physical systems. While these experiments don't create real warp drives or wormholes, they help scientists understand the underlying physics more deeply. And even if faster than light travel through bending space remains far beyond reach, The process of studying these ideas often leads to unexpected discoveries. Many technologies we rely on today, from lasers to semiconductors to GPS systems, grew out of research that initially seemed purely theoretical. So the question of bending space isn't only about reaching distant stars. It's also about understanding the universe at a deeper level, exploring the limits of what physics allows, and learning how space-time itself behaves under extreme conditions. There's something quietly fascinating about the thought that space, which feels so solid and unchanging in everyday life, is actually flexible. It can stretch, ripple, and curve. Massive objects shape it. Energy flows through it. Gravitational waves, first detected in 2015, travel across the cosmos as tiny vibrations in space-time itself, produced by collisions of black holes billions of years ago. We're living in a universe that's far more dynamic than it appears at first glance. And yet, even with all this flexibility, bending space in the ways required for faster-than-light travel remains an enormous challenge. The equations allow it in principle, but the practical hurdles seem almost insurmountable. Perhaps that's fitting, though. The universe reveals its secrets slowly, keeping its deepest mysteries just beyond our current reach, always inviting us to push a little further into the unknown. The cosmos has always been stubborn about revealing its secrets. Throughout history, we've had this peculiar habit of declaring things impossible, only to watch those impossibilities quietly slip into reality decades later. Flight was once unthinkable, splitting atoms belonged to fantasy, and machines traveling to other planets lived only in stories. This pattern teaches us something profound about the nature of human understanding and our relationship with the impossible. When physicists today talk about bending space itself, they're exploring territory that feels equally impossible. Yet the mathematics whispers intriguing possibilities. The very fact that we can ask these questions, that we can explore them with equations and concepts, reveals something beautiful about human curiosity. We're creatures compelled to push against the boundaries of what seems possible. Einstein's general relativity gave us a startling insight about the universe. Space and time aren't rigid, unchanging things. They stretch, compress, and curve in response to mass and energy. What we experience as gravity isn't really a pulling force, but rather the result of this curvature guiding how objects move through space. Stars and planets naturally bend space-time around themselves, creating the gravitational effects we observe. This realization naturally leads to an intriguing question. If space-time bends naturally around massive objects, could we perhaps shape it deliberately? This idea forms the foundation of what physicists call warp-drive physics. It's not science fiction anymore, but a legitimate area of mathematical exploration. In 1994, a Mexican physicist named Miguel Alcubierre made a fascinating discovery. He wasn't trying to design an actual spacecraft, but rather studying Einstein's field equations to understand what kinds of spacetime geometries those equations allow. What he found was genuinely surprising. There exists a mathematical solution where a region of spacetime forms a kind of moving bubble. Inside this hypothetical bubble, spacetime remains relatively flat and calm. Outside it, something remarkable happens. Space in front of the bubble contracts while space behind it expands. The bubble itself moves forward, carried by this distortion of spacetime itself. The spacecraft inside wouldn't be moving through space in the ordinary sense. Locally, it would remain at rest relative to the spacetime around it. From the crew's perspective, there would be no sensation of crushing acceleration, no forces pressing them into their seats. Yet to distant observers, the bubble could travel faster than light. The cosmic speed limit wouldn't be violated locally because nothing inside the bubble would be outrunning light in its immediate surroundings. Instead, the distance between starting point and destination would shrink and expand in ways that effectively allow faster than light travel. Think of a small coin resting on a sheet of rubber. If you stretch the rubber behind the coin and compress it in front, the coin moves forward without ever sliding across the surface. The surface itself carries it along. In warp-drive physics, spacetime plays the role of that flexible surface. It's an imperfect analogy, but it captures something essential about how this might work. At first glance, this seems almost too convenient, like finding a loophole in the laws of physics, but the mathematics remains consistent with general relativity. The equations don't forbid such a geometry. What they do reveal, however, is that creating this geometry requires something extraordinary. The original Alcubierre solution showed that forming a warp bubble would require negative energy density, sometimes described as exotic matter. This isn't merely an unfamiliar material. It's a form of energy that behaves opposite to anything we encounter in daily life. Ordinary matter has positive energy density and contributes to gravitational attraction. Negative energy density would produce gravitational effects that could be described as repulsive in certain contexts. It's precisely this unusual behavior that would allow space-time to be shaped into the necessary configuration for a warp bubble. So naturally, we must ask whether negative energy actually exists. In everyday experience, the answer appears to be no. We don't find lumps of negative energy lying around, and no known material has this property on large scales. However, quantum physics introduces some subtle exceptions. One example is the Casimir effect, a phenomenon observed when two metal plates are placed extremely close together in a vacuum. Quantum fluctuations in the vacuum create a tiny force that can be interpreted as arising from a region of negative energy density between the plates. This effect is real and measurable, but extraordinarily small. The amount of negative energy involved is far too tiny to power anything resembling a warp drive. It's like finding a single drop of water and being asked to fill an ocean. Early calculations suggested that the energy required for a warp bubble, large enough to hold a spacecraft, might be comparable to the mass energy of an entire planet, or even larger. Later studies refined the model and found ways to reduce the requirement, but it remains immense by any practical standard. Energy is only part of the challenge, though. There's also the question of stability. A warp bubble isn't a static object. It's a dynamic distortion of spacetime that must be maintained continuously. Even small disturbances could cause the bubble to collapse or behave unpredictably. The mathematics describing these instabilities is complex, and researchers are still working to understand them fully. Another issue involves the boundary of the bubble itself. Some analyses suggest that enormous amounts of energy could accumulate at the front edge of a warp bubble as it moves, potentially in the form of high-energy particles or radiation. When the bubble slows or stops, this energy might be released in a burst, posing a hazard to whatever lies ahead. This raises an uncomfortable possibility. A warp drive, arriving at its destination, might unintentionally deliver a surge of radiation, not exactly the sort of greeting one would hope for when visiting another star system. There's also a more subtle problem involving causality and control. In certain models, the region of spacetime at the front of the warp bubble lies outside the causal influence of the interior. In simpler terms, signals from inside the bubble might not be able to reach the front edge to control or steer it. That would make navigation extremely difficult, perhaps impossible. Imagine driving a car where the steering wheel cannot influence the front wheels. The vehicle might move, but directing it would be another matter entirely. These difficulties don't necessarily mean warp drives are impossible. They do show that the gap between mathematical possibility and practical engineering is enormous. Researchers continue to explore variations of the idea. Some have proposed alternative geometries that reduce the amount of negative energy required. Others have investigated whether quantum effects might provide new ways of generating or stabilizing exotic energy densities. There's also interest in analog systems, experiments that simulate aspects of spacetime behavior using materials or fields that mimic certain mathematical properties. These experiments don't create real warp bubbles, but they help physicists understand how waves and disturbances propagate in curved geometries. Beyond the technical challenges, there's a deeper question about the nature of spacetime itself. General relativity describes spacetime as smooth and continuous. But at extremely small scales, quantum effects are expected to become important. A complete theory of quantum gravity, which physicists are still searching for, might reveal new features of spacetime that could change our understanding of what's possible. Relativity itself was once a radical idea, challenging assumptions that had seemed obvious for centuries. The discovery that time can slow down and length can contract wasn't something anyone had anticipated. It emerged from careful reasoning and experimental evidence. While warp drives remain speculative, the study of such ideas serves a valuable purpose. It pushes the boundaries of our understanding and forces us to examine the fundamental laws of nature more closely. There's something quietly fascinating about the perspective warp drive physics offers on distance. We're accustomed to thinking of distance as fixed, an unchangeable separation between 2 points. But in general relativity, distance depends on the geometry of spacetime, and geometry can change. The universe itself provides an example. During the earliest moments after the Big Bang, space expanded at an extraordinary rate in a process known as cosmic inflation. Regions of space moved apart faster than light, not because objects were racing through space, but because space itself was stretching. That event happened on a scale far beyond anything we could hope to reproduce, but it demonstrates that space-time is capable of behavior far stranger than everyday experience suggests. Even with all these possibilities, the practical obstacles remain daunting. Generating the required energy, controlling the geometry of space-time, protecting passengers from radiation and collisions, navigating across interstellar distances, each of these challenges is formidable on its own. Together, they form a barrier at least as imposing as the speed of light itself. Perhaps the most honest conclusion at present is that warp drives are allowed by certain interpretations of the equations, but far beyond our current technological reach. They're not impossible in the strict mathematical sense, but neither are they close to becoming reality. There's a quiet kind of beauty in that uncertainty. Science doesn't always provide clear answers. Sometimes it offers a landscape of possibilities, some near, some distant, some perhaps forever out of reach. This ambiguity reflects something profound about our place in the universe, creatures of curiosity standing at the edge of the known, peering into the vast unknown that surrounds us. Space-time might already hold secrets we're only beginning to glimpse. Hidden connections that link distant places through routes shorter than ordinary geometry would suggest. When physicists first realized that gravity could bend and warp the very fabric of space and time, a remarkable possibility emerged. If the universe's geometry can be curved, then perhaps some regions might connect in ways that aren't immediately obvious to us. Picture a simple sheet of paper with 2 dots drawn on opposite edges. Following the surface, you'd measure quite a distance between them, but fold that paper so the dots nearly touch, and suddenly they're almost neighbors. That folding represents something profound about how space itself might work. The paper stands for space-time, and the fold shows us how shortcuts might exist where flat thinking says they shouldn't. Real space-time isn't paper, of course, and we can't fold it with our hands, but Einstein's equations describe a universe with flexible geometry. When mathematicians dove deep into those equations, they found solutions that looked like tunnels connecting far apart regions. These became known as wormholes, a term that paints a vivid picture. Think of an apple with a worm boring straight through its center. The worm's tunnel offers a shortcut from one side to the other, much faster than crawling around the surface. Back in the 1930s, Einstein worked with Nathan Rosen to study one particular solution that seemed to bridge separate regions of space-time. This Einstein-Rosen bridge was mostly mathematical curiosity at first. Nobody knew if such things could actually exist, or if they'd collapse too quickly for anything to pass through. Later research suggested most wormhole solutions would be unstable, pinching shut almost instantly due to gravitational forces. They'd be more like brief ripples than usable highways. The story took an interesting turn in the late 20th century, when physicists wondered if certain conditions might keep a wormhole open. The key seemed to be exotic matter, stuff with negative energy density. This theoretical material could counteract the natural collapse, holding the tunnel's throat open long enough for passage. But here's where things get philosophically intriguing. The mathematics allows for possibilities that physical reality might not provide the ingredients for. There's also the question of how wormholes might form naturally. Some theories suggest tiny ones could pop up at incredibly small scales, due to quantum fluctuations in space-time itself. This hypothetical quantum foam would involve structures unimaginably small and short-lived, nowhere near anything we could enlarge or use for travel. Other ideas propose they might form in extreme environments, maybe near black holes or during the universe's earliest moments. Astronomers have searched for signs that might distinguish a wormhole from a black hole, looking for unusual gravitational lensing patterns. But every candidate so far has turned out consistent with ordinary black holes. Even if we found or created a stable wormhole, practical challenges would be enormous. Tidal forces near the throat could be devastating, stretching and compressing anything trying to pass through like cosmic taffy. Navigation presents its own puzzle. A wormhole connects two regions of space-time, but figuring out exactly where those regions are and ensuring the exit leads where you want would be incredibly complex. Space isn't static after all. Stars drift, galaxies spin, the universe expands. Wormhole entrances and exits would need careful alignment, or travelers might emerge in empty interstellar void, far from any warming star. Perhaps most fascinating is how wormholes might relate to time itself. Under certain conditions, they could theoretically allow travel through time as well as space. If one end experienced time dilation, maybe by moving at high speed or sitting in a strong gravitational field, the two ends could become offset temporally. Passing through might let you emerge in the past or future, relative to your entry point. This raises mind-bending paradoxes that physicists have explored extensively. Some theories suggest the laws of physics might prevent such paradoxes by forbidding the necessary conditions. Others propose multiple timelines, or self-consistent histories, could resolve contradictions. These ideas remain speculative, but they show how wormholes challenge our understanding of causality and reality structure. Importantly, wormholes wouldn't require spacecraft to travel faster than light locally. The speed limit of relativity stays intact. The apparent faster-than-light travel comes because the wormhole path is shorter than the normal space route. From a traveler's perspective, the journey might take hours while light traveling outside would need years. This subtle distinction shows the universe might permit shortcuts without letting objects outrun light in their immediate surroundings. Despite enormous challenges, wormholes remain an active research area. Physicists study their properties using general relativity, quantum field theory, and emerging quantum gravity ideas. Recent work has even explored connections between wormholes and quantum entanglement, suggesting space-time geometry and quantum information might link in ways we're just beginning to understand. These developments don't bring practical wormholes closer to reality, but they deepen our cosmic understanding. Sometimes an idea's value lies not in immediate application, but in insights gained along the way. There's something quietly profound about contemplating these possibilities. The universe stretches beyond measure, yet physics allows for structures that could bridge enormous distances. Whether such structures exist or not, the fact we can imagine and study them reminds us reality is often richer than first impressions suggest. It's important to maintain perspective though. Wormholes, if they exist, aren't waiting beyond Pluto for discovery by our next spacecraft. They remain hypothetical, supported by mathematics, but not observation. When we consider ideas like warp drives and wormholes seriously, the conversation shifts to more grounded questions. What would it actually take to make them real? Not just mathematically consistent, but physically possible. Not just imaginable, but buildable. This is where discussion becomes less about geometry and more about energy, matter, and physics, stubborn realities. Every motion change requires energy. Accelerating a bicycle needs muscle energy. Launching rockets demands enormous chemical fuel energy. Sending spacecraft to other planets requires still more because gravity must be overcome and high speeds reached. Energy is the universe's price for doing anything. When it comes to bending space-time, that price rises dramatically. General relativity tells us mass and energy determine space-time curvature. The stronger curvature you want, the more mass energy you must concentrate. A person produces almost imperceptible curvature. A planet produces more. A star, much more. Black holes produce curvature so extreme that even light can't escape past the event horizon. Warp drives and traversable wormholes would require spacetime distortions far beyond ordinary astronomical bodies. Those distortions would need controlled, sustained precision. Early calculations for Alcubierre warp drives suggested creating a bubble large enough for a modest spacecraft might require energy comparable to Jupiter's total mass energy. Later refinements reduced estimates, but even optimistic scenarios demand energy far beyond anything humanity has produced. To grasp this scale, consider that human civilization's total energy consumption pales beside what these concepts would require. The sun releases more energy in a single second than all of human civilization has consumed throughout our entire history. Think about that for a moment. Every power plant, every fire, every machine we've ever built, all of it combined, doesn't match what our star casually throws off in the time it takes you to blink. This puts things in perspective when we talk about the energy needed for faster-than-light travel. The energy requirements for a warp drive don't just exceed what we produce today, they approach the scale of stars themselves. A large nuclear explosion, devastating as it might be, represents a tiny fraction of what we'd need. Even all the energy humanity produces in an entire year would be insignificant compared to what's required. We're not talking about building bigger power plants. We're talking about harnessing forces that dwarf entire civilizations. But here's where it gets truly strange. The amount of energy isn't even the biggest problem. The type of energy we need is something far more exotic. Most theoretical models for warp drives require what physicists call negative energy density, or exotic matter. This isn't just a lot of ordinary fuel burned in a different way. This is energy that behaves in fundamentally opposite ways to everything we know. Normal matter, the stuff that makes up stars and planets and you and me, has positive energy density. It attracts things gravitationally, pulling them together. Exotic matter would work backwards. It would have negative energy density, creating gravitational effects that appear to push things apart. This would allow space and time to curve in the opposite direction from what we normally see. At first glance, this sounds like pure science fiction. Yet physics gives us tiny hints that such things might be possible. There's something called the Casimir effect that demonstrates this in the smallest possible way. When you place two metal plates incredibly close together in a vacuum, quantum fluctuations in the electromagnetic field create a measurable force pulling them together. The mathematics describing this can be interpreted as showing a region of negative energy density between those plates. The key word here is tiny. We're talking about effects so small they barely register in the most sensitive laboratory equipment. The amount of negative energy involved is so minuscule, it has no practical application beyond proving the concept exists, but it does show that the universe allows negative energy in very limited forms. Whether we could ever produce it in large quantities or control it remains completely unknown. Most physicists suspect there are strict limits on how much negative energy can exist and for how long. These restrictions come from principles called quantum inequalities, which seem to bound the magnitude and duration of negative energy regions. In simple terms, the universe appears willing to allow small violations of normal energy rules, but not large or sustained ones. This creates a serious problem for warp drives, which would need large amounts of negative energy maintained over extended periods. Even if we could create exotic matter, how would we store it or shape it? Ordinary matter can be held in tanks or contained with magnetic fields. Exotic matter might not behave in ways that allow any kind of straightforward containment. Its gravitational effects could be wildly unpredictable, and small disturbances might grow rapidly out of control. There's also the question of how exotic matter would interact with normal matter. Would it repel ordinary objects gravitationally? Would it interact electromagnetically at all? These remain largely theoretical questions because no macroscopic samples of exotic matter have ever been observed or created. We're essentially designing engines for a fuel that might not be able to exist in useful quantities. Energy requirements also raise questions about efficiency. In every physical process we know, Some energy gets lost as heat or radiation. Maintaining a warp bubble or stabilizing a wormhole would likely require continuous energy input, not just a one-time investment. The total energy budget could be far larger than initial estimates suggest. We might need to feed these systems constantly, like keeping a fire burning, but with energy outputs that rival stars. Then there's the matter of actually building something, which often proves as challenging as the underlying physics. Even when a theoretical mechanism exists, translating it into a practical device involves materials, structures, control systems, and safety considerations that can take decades or centuries to develop. History gives us plenty of examples of this gap between theory and practice. Heavier-than-air flight was understood in principle long before the Wright brothers actually got off the ground. Nuclear energy was predicted by theory years before anyone built a working reactor. Controlled fusion has been theoretically possible for decades, but remains technologically elusive. Warp drives might belong to this same category, but at a much greater scale of difficulty. The picture gets even more complicated when we consider the interaction between quantum mechanics and general relativity. These two pillars of modern physics work extremely well in their respective domains, but they haven't been fully unified into a single theory. At very small scales or very high energies, we may need a complete theory of quantum gravity to understand how space and time actually behave. Such a theory might reveal new constraints that completely forbid macroscopic warp drives and wormholes. It's also possible, though less widely expected, that it could reveal new mechanisms making them more feasible. At present, we simply don't know which way the physics will point. There's also the matter of observational evidence, or rather, the lack of it. So far, no natural phenomena have been conclusively identified as stable wormholes or warp-like structures. We've observed black holes, neutron stars, and gravitational waves, but none show the specific properties required for faster-than-light shortcuts. This absence doesn't prove impossibility, but it suggests that such structures, if they exist at all, are extremely rare or difficult to form naturally. The timescale of technological progress adds another layer of complexity. Human civilization has advanced rapidly in many areas, but the gap between our current capabilities and the requirements of space-time engineering is staggering. Generating energies comparable to stellar outputs, manipulating exotic matter, and controlling the geometry of space-time would require technologies far beyond anything we can currently imagine. Yet scientific progress often occurs in unexpected ways. New discoveries can open paths that were previously invisible. The development of lasers, semiconductors, and nuclear magnetic resonance all arose from fundamental research that had no immediate practical goal. Sometimes studying the limits of physics leads to new tools and technologies, even when the original dream remains out of reach. There's something profound about our fascination with faster-than-light travel. It appeals to us not only because it would let us reach distant stars, but because it challenges our understanding of what's possible. It forces us to ask what aspects of reality are truly fundamental, and which might be more flexible than we assume. Even if warp drives and wormholes never become practical, the effort to understand them deepens our grasp of space, time, energy, and the quantum nature of reality. We're pushed to explore the boundaries of knowledge, to test our assumptions about how the universe works. There's value in that exploration, regardless of whether it leads to working starships. At the same time, there's a certain wisdom in acknowledging the scale of the challenge we face. The universe doesn't reshape itself easily. The laws of physics permit remarkable phenomena, but they also impose constraints that aren't easily bypassed. The problem of energy and exotic matter remains one of the greatest barriers to faster-than-light travel. We're not just talking about building better engines or larger spacecraft. We're talking about discovering entirely new forms of matter and energy, then learning how to manipulate the fabric of space and time itself. Still, the exploration continues, and each new study adds another small piece to an enormous puzzle. Whether that puzzle will ever be completed in a way that allows practical faster-than-light travel remains to be seen. But the journey of trying to solve it continues to reveal new depths in our understanding of reality itself. The universe holds secrets about time that challenge everything we think we know about cause and effect. When scientists dig deeper into the possibility of traveling faster than light, they uncover layers of complexity that go far beyond engineering problems. The questions shift from what kind of energy we might need to something much more profound, whether the very fabric of reality would allow such journeys to exist. Think about how naturally we experience the flow of time in our daily lives. You press a button, then a machine starts running. You knock over a cup, then it falls to the ground. This sequence feels so obvious, so fundamental, that we rarely question it. But what if this order, this steady march from cause to effect, could be disrupted? What if the universe operates by rules that are stranger than our intuition suggests? Einstein's relativity reveals that time isn't the fixed, universal backdrop we imagine it to be. Two people moving at different speeds through space will actually disagree about when certain events happen. What looks simultaneous to one person might appear to occur in sequence to another. This sounds impossible, yet it's been measured and confirmed countless times. GPS satellites have to account for these differences just to keep our navigation systems working properly. Here's where things get really interesting though. As long as nothing travels faster than light, this flexibility in time doesn't create contradictions. The speed of light acts like a cosmic speed limit that keeps the order of events intact. Information can't arrive somewhere before it was sent, at least not from anyone's perspective. But remove that speed limit, and the careful balance starts to unravel. Imagine sending a message to a distant star, faster than the speed of light. From your point of view, the message travels forward through time, reaching its destination after you sent it. But because of how space and time are woven together, someone else, moving relative to you, might observe that message arriving before you even sent it. If they then reply, using the same faster-than-light technology, their response could reach you before you asked your original question. You'd be holding an answer to something you haven't thought of yet. This isn't science fiction speculation. It emerges directly from the mathematical relationships that govern space and time. Once you allow faster-than-light travel, you open the door to scenarios where effects can precede their causes. The implications ripple outward into some of the most famous puzzles in theoretical physics. Consider the grandfather paradox, though it doesn't have to involve grandparents or family drama. The core issue is simple but profound. If you could travel backward in time and prevent some event that was necessary for your own existence, you create a logical loop that contradicts itself. You couldn't have made the journey if the event you prevented had been prevented. The sequence eats its own tail. Physicists take these paradoxes seriously, not because they're planning to build time machines, but because contradictions in physical laws usually signal that something fundamental is misunderstood. When the mathematics leads to impossible situations, it often means we need to reconsider our assumptions. Several elegant solutions have been proposed to resolve these temporal puzzles. One idea suggests that space-time itself might be self-correcting. If time travel were possible, events would automatically arrange themselves to avoid contradictions. You might try to change the past, but circumstances would always conspire to prevent paradoxical outcomes. Coincidences would occur. Obstacles would appear. The universe would protect its own consistency. Another approach comes from quantum mechanics, and the idea that reality might branch into multiple timelines. In this picture, traveling into the past wouldn't change your own history, but would instead shift you into a different version of reality. Every possible outcome would exist in its own separate branch, and contradictions would be avoided because the different timelines wouldn't interfere with each other. These concepts are mathematically sophisticated and intellectually appealing, but they remain purely theoretical. We have no experimental evidence that such mechanisms actually operate in our universe. There's also a more conservative possibility that the laws of nature simply forbid situations that would create paradoxes in the first place. This idea, sometimes called chronology protection, suggests that quantum effects or other physical mechanisms prevent the formation of paths through spacetime that would allow objects to return to their own past. The universe, in effect, guards its own history. Conditions that would enable paradoxes never arise because the underlying physics prevents them from occurring. Even setting aside paradoxes, faster-than-light travel would introduce other complications that are worth considering. Some theoretical models suggest that enormous amounts of energy could accumulate along the path of a spacecraft using exotic propulsion methods. If this energy were released suddenly, it could create serious hazards, not just for travelers, but for anything near their destination. Navigation would become extraordinarily challenging when dealing with severely distorted spacetime. Small errors in calculation could lead to massive deviations in position or arrival time. A spacecraft emerging even slightly off course in the vast emptiness between stars could find itself stranded, far from any planet or source of help, with limited resources and no easy way to correct the mistake. Communication systems would face unprecedented difficulties too. Signals sent faster than light could arrive out of sequence, or interfere with each other in unpredictable ways. Coordinating activities across interstellar distances might become more complicated rather than simpler. Despite the faster speeds involved, there are human considerations as well, ones that can't be captured in equations. Traveling at extreme speeds, or through regions where spacetime is severely warped, would separate travelers from the normal flow of time experienced by everyone else. Even without exceeding light speed, time dilation effects mean that years or decades could pass on Earth while only months pass for a spacecraft crew. Returning home after such a journey wouldn't simply be a matter of landing and picking up where you left off. It would mean arriving in a future where friends and family had aged or died, where society had transformed, where the world you remembered existed only in history. That's a different kind of risk entirely, one that touches on questions of meaning, identity, and what it means to be human in a universe where time itself can be bent. At the same time, physics has a long history of revealing possibilities that seemed impossible, at first but gradually became familiar as our understanding deepened. Time dilation was once considered a strange mathematical prediction, but now it's routinely accounted for in satellite navigation. Black holes were once dismissed as mathematical curiosities, but now we observe them throughout the cosmos, and even photograph their shadows. The fact that faster-than-light travel raises paradoxes doesn't automatically prove it's impossible, but it does mean that any theory allowing such travel must address these paradoxes in a logically consistent way. The mathematical framework has to work, the physics has to make sense, and the implications have to be reconciled with everything else we know about how the universe operates. For now, the weight of evidence suggests that the speed of light represents more than just a practical barrier. It appears to be woven into the fundamental structure of causality itself. Crossing that limit might not simply be difficult from an engineering perspective. It might require a completely different understanding of time, space, and the relationships between events. The research continues, though, with scientists refining theoretical models, testing predictions, and searching for clues in both mathematical theory and astronomical observation. Each new discovery adds another piece to this cosmic puzzle, bringing us closer to understanding whether the universe will ultimately allow us to exceed its most famous speed limit, or whether that boundary exists to preserve something even more fundamental, the logical consistency of reality itself. The scientific journey toward understanding what lies beyond our cosmic speed limit continues to unfold in laboratories and observatories around the world. Researchers keep pushing the boundaries, not because they expect to break through tomorrow, but because the universe has this peculiar habit of defying our expectations. What seemed impossible yesterday sometimes becomes reality today, while other dreams remain forever tantalizing, just out of reach. The story of modern physics and faster-than-light travel sits in this strange middle territory, neither promising nor completely dismissing such possibilities. Think about how unsettling this must be for scientists, who prefer clear answers. Instead, they find themselves exploring a landscape where theory whispers maybe, while practical reality shouts not yet, possibly never. Relativity theory stands like an ancient fortress, tested countless times and never breached. Every particle accelerator on Earth pushes matter to incredible speeds, racing electrons and protons around circular tracks. But these particles always hit that same invisible wall, the speed of light. Cosmic rays, the most energetic particles nature hurls across space, follow the same rules. They streak through the cosmos at nearly light speed, but never beyond it. This consistency carries weight in science, like testimony from thousands of witnesses, all telling the same story. When a principle holds across laboratory experiments and cosmic observations, from the smallest scales to the largest, confidence builds slowly, methodically. The speed of light limit has become more than theory, it's become a verified feature of reality itself. Yet the universe plays interesting games with this limit. Space itself expands, carrying distant galaxies away from us faster than light, not through motion, but through the stretching of space-time itself. This phenomenon emerged from careful observations of the cosmic microwave background, that ancient light still glowing from the early universe. Red-shifted galaxies tell us the same story, their light stretched by expansion during its billion-year journey to our telescopes. Here's where things get philosophically interesting. The universe allows certain behaviors that seem to violate the speed limit without actually breaking the rules. It's like discovering loopholes in the laws of physics, written in fine print, that we're still learning to read. Gravitational waves add another chapter to this story. When massive black holes spiral into each other, they create ripples in space-time that travel at exactly the speed of light. Scientists detected these waves directly in 2015, measuring both the gravitational ripples and the light from the same cosmic collision. Both arrived at Earth at virtually the same moment, confirming once again that information cannot outrun light. Quantum mechanics introduces its own puzzles. Entangled particles seem to communicate instantly across vast distances, their properties mysteriously correlated no matter how far apart they drift. Scientists have tested this with particles separated by kilometers, even using satellites to create entangled pairs. Across continents, the correlations appear immediately. But here's the catch: they cannot carry useful information faster than light. Nature seems almost mischievous in this regard. It allows instant correlations while preventing instant communication. The mathematics reveal this distinction clearly, but it took decades of careful experiments to understand what quantum entanglement actually permits and what it forbids. Deep down at the smallest possible scales, space-time itself might not be smooth, but granular, fluctuating in ways we cannot directly observe. Some theories suggest that at the Planck scale, distance is so tiny they make atoms look enormous. Reality might behave very differently. Whether these quantum fluctuations could somehow enable faster-than-light phenomena remains unknown. Theoretical physicists continue studying exotic solutions to Einstein's equations, mathematical descriptions of warped space-time that might, in principle, allow faster-than-light. Recent papers have proposed modifications to warp drive concepts that require less exotic energy, though still far beyond anything we can produce. These microscopic warp bubbles remain purely theoretical, existing only in equations. The gap between mathematical possibility and physical reality yawns wide here. It's like finding a recipe for flying carpets that requires ingredients that don't exist. The mathematics might work perfectly while remaining completely impractical. Energy conditions and quantum inequalities place further constraints on these exotic phenomena. Nature seems to resist the extreme configurations required for faster-than-light travel, as if the universe has built-in safeguards against such disruptions to causality. From an astrophysical perspective, the absence of evidence becomes evidence itself. If faster-than-light travel were achievable for advanced civilizations, we might expect to see signs of it in our astronomical observations. Unusual energy signatures, large-scale engineering projects, or strange patterns of motion might reveal such technologies. The cosmic silence on this front suggests that even civilizations far more advanced than ours have not mastered such capabilities. This leads to a humbling realization. The universe might be vast beyond imagination, filled with countless worlds and civilizations, yet all of them bound by the same fundamental limits that constrain us. We share cosmic loneliness, not through lack of company, but through shared imprisonment within the speed of light barrier. Modern physics maintains a careful balance between skepticism and openness. History teaches us that nature loves surprising us. Quantum mechanics once seemed absurd. Space-time flexibility appeared impossible. and gravitational waves remained theoretical curiosities for a century before detection. Scientists have learned to say that faster-than-light travel appears forbidden under current understanding, while leaving room for future revelations. Alternative approaches to interstellar travel focus on reaching significant fractions of light speed rather than exceeding it. Laser-driven light sails, nuclear fusion rockets, and antimatter engines representing engineering challenges rather than physics impossibilities. Projects like tiny interstellar probes accelerated by powerful laser arrays have moved from science fiction to serious research proposals. These modest goals carry their own profound implications. Even without faster-than-light travel, humanity could eventually spread throughout the galaxy through patience and ingenuity. Generation ships, self-sustaining spacecraft carrying entire communities across centuries of travel, could bridge the vast distances between stars. The universe does not forbid interstellar exploration. It simply demands time and determination. Looking toward the future, our understanding of fundamental physics remains incomplete. A complete theory of quantum gravity, if ever achieved, might reveal new principles that reshape our conception of what nature allows. Space-time itself might possess properties we have not yet discovered, hidden layers of reality waiting for the right theoretical breakthrough or experimental technique. The question of faster-than-light travel serves a valuable purpose beyond its practical implications. It pushes scientists to explore the deepest foundations of reality, the relationship between space and time, matter and energy, cause and effect. Even if the dream remains forever out of reach, the journey of investigation brings unexpected discoveries and deeper understanding. There's something both reassuring and melancholic about these cosmic speed limits. They provide stability and consistency to physical law, allowing us to build technologies and make predictions with confidence. Yet they also impose a kind of cosmic loneliness, making the universe feel both infinite in scope and intimate in its fundamental constraints. Perhaps the most profound realization is that the same laws of physics that light forever prevent faster-than-light travel also enable the complex chemistry of life, the nuclear fusion of stars, and the formation of planets. The universe's consistency creates both possibilities and limitations, and we exist within both. The universe stretches out before us, filled with distances that challenge our imagination. When we think about traveling to other stars, we often assume we need to break the speed of light. But modern physics tells us something different, something more hopeful. We don't need to travel faster than light to reach the stars. We just need to travel fast enough. The nearest star to our Sun, Proxima Centauri, sits about 4¼ light-years away. That distance represents a journey of staggering proportions. If we could somehow push a spacecraft to 10% of light speed, the trip would still take over 40 years. Double that speed to 20%, and we're looking at roughly 20 years. These aren't impossible timeframes, not really. They're long, yes, but they fall within the span of a human lifetime. The real challenge isn't time, it's energy. Chemical rockets, the kind that have carried us to the moon and beyond, simply can't provide the massive amounts of energy needed for interstellar flight. They work beautifully for missions within our solar system, but asking them to accelerate a large spacecraft to a significant fraction of light speed, that's like asking a bicycle to compete in a Formula One race. Nuclear reactions change everything about energy. When atoms split apart in nuclear fission, they release far more energy per unit of mass than any chemical reaction ever could. A nuclear rocket could heat its propellant to temperatures that would make conventional rockets look like gentle candles. Engineers studied these concepts back in the middle of the 20th century. They never flew, but the physics behind them, that's solid, even more powerful than fission, is fusion, the same process that makes stars shine. When light atomic nuclei combine, they release enormous amounts of energy. In the 1970s, scientists designed a theoretical spacecraft called Daedalus. It would use tiny pellets of fusion fuel, ignited in rapid succession, to produce thrust. The design could reach a significant fraction of light speed, at least on paper. Fusion propulsion faces a stubborn problem though. We still haven't figured out how to make controlled fusion produce more energy than it consumes, at least not on a practical scale, but research continues. and many physicists believe fusion reactors will eventually work. When that happens, fusion-powered spacecraft might become more than just dreams on drawing boards. Antimatter takes the energy gain to its absolute limit. When matter meets antimatter, they don't just react, they annihilate completely. All of their mass converts directly into energy, following Einstein's famous equation. An antimatter engine could theoretically produce exhaust velocities that would make fusion look sluggish. The catch with antimatter isn't physics, it's practicality. Creating antimatter requires enormous amounts of energy, and storing it safely demands complex magnetic confinement systems. Current methods produce only microscopic amounts at costs that would bankrupt small countries. Scaling this up to spacecraft levels would be, well, formidable doesn't begin to cover it. But there's another approach entirely, one that sidesteps the whole fuel problem. Instead of carrying energy with you, why not leave the power source at home? Powerful lasers or particle beams could push against a light sail, a large reflective structure that captures momentum from photons. The spacecraft itself could be incredibly light because it doesn't need to carry fuel. Some researchers are actually exploring this idea right now. They're proposing to send tiny probes, weighing just a few grams, to nearby stars using laser-driven sails. These miniature spacecraft could reach 20% of light speed and arrive at their destinations within decades. They couldn't carry human passengers, but they could send back data, images, and measurements from another star system. When spacecraft reach significant fractions of light speed, something interesting happens to time itself. Time dilation, a consequence of special relativity, means that time passes more slowly for objects moving at high speeds. At 10 or 20% of light speed, the effect is modest but measurable. For travelers on board, a journey lasting decades on Earth might feel somewhat shorter, depending on their exact speed. This doesn't eliminate the long travel times entirely, but it changes the experience in subtle ways. Time becomes relative in the most literal sense, stretching differently for those who stay and those who go. Not everyone thinks we need to reach extreme speeds, though. Generation ships represent a completely different philosophy of interstellar travel. These massive vessels would travel slowly, perhaps only a few % of light speed, carrying entire, self-sustaining communities. The journey might take centuries, with multiple generations living and dying on board before arrival. This idea raises fascinating questions that go far beyond engineering. How would a community maintain its knowledge and sense of purpose over such a long voyage? How would resources be managed across generations who never chose to make the journey? These aren't purely scientific questions, but they're essential to understanding how such missions might actually work. Another possibility involves suspended animation or hibernation. If astronauts could be placed in a state of greatly reduced metabolism, similar to what some animals do naturally, they might endure long journeys without experiencing the full passage of time. Medical research into hibernation continues, though it's still far from being ready for long-duration spaceflight. Robotic exploration might prove the most practical approach, at least initially. Machines don't need life support systems. They can operate for decades or longer, and they can tolerate conditions that would kill humans instantly. Advances in artificial intelligence could allow robotic probes to conduct complex investigations far from Earth, making decisions and solving problems without waiting years for instructions from home. Some theorists have proposed self-replicating probes, sometimes called von Neumann probes. These machines could use local materials in a star system to create copies of themselves, then continue exploring other systems. While this remains theoretical, it illustrates how exploration might proceed without requiring faster-than-light travel or direct human presence. Traveling at high speeds through space introduces hazards that Earthbound travelers never face. Even tiny particles of dust become dangerous projectiles when you're moving at a significant fraction of light speed. Their kinetic energy increases dramatically with velocity. Spacecraft would need shielding capable of absorbing or deflecting these impacts without being destroyed. Radiation presents another serious concern. Cosmic rays and high-energy particles pose risks to both electronic systems and biological tissues. Long-duration missions would require robust protection, possibly involving new materials or magnetic shielding technologies that don't exist yet. Navigation over interstellar distances creates its own unique challenges. Space offers few landmarks for reference. Spacecraft would need incredibly precise instruments to determine their position and trajectory over journeys lasting decades or centuries. Communication delays would be substantial too. Messages traveling at light speed would take years to cross the distance between stars, making real-time mission control impossible. These difficulties are real, but they don't violate any known laws of physics. All of the concepts we've discussed, fusion rockets, antimatter engines, laser sails, generation ships, they all operate within the boundaries of established science. They require advances in technology, not revolutions in our understanding of the universe. There's something quietly encouraging about that realization. The universe may be vast beyond comprehension, but it's not completely inaccessible to us. The laws of physics permit travel between stars, even if such journeys require patience, ingenuity, and probably centuries of technological development. Human exploration has often proceeded in stages anyway. Early sailors crossed oceans without knowing what lay beyond the horizon. Later generations built faster ships, then aircraft, then spacecraft. Each step seemed extraordinary at the time, yet eventually became part of ordinary experience. Interstellar travel might follow a similar pattern. The first missions would probably involve small robotic probes, gathering basic information about nearby star systems. Later missions could involve larger automated spacecraft, perhaps carrying biological systems to distant worlds. Human journeys, if they happen at all, would likely come much later, when our technology and understanding have advanced far beyond their current state. By then, what seems impossible today might seem routine to future generations. The drive to explore appears to be fundamental to human nature. It has carried us across continents, over oceans, and into orbit around our planet. That same curiosity, that same restless desire to see what lies beyond the next horizon, may eventually carry us to the stars, even without faster-than-light travel. And perhaps that raises the most interesting question of all. If humanity does develop the ability to travel between stars, even slowly, how would that change our civilization, our culture, our entire understanding of what it means to be human in an infinite universe? The universe we inhabit is fundamentally shaped by the cruel mathematics of distance and time. Light itself, racing across the void at nearly 300 million meters per second, takes over 4 years to reach us from the nearest star. This creates what we might call a prison of isolation, where humanity remains confined to a single pale blue dot, surrounded by an ocean of emptiness that stretches beyond comprehension. Consider for a moment what this really means. Our fastest spacecraft would need tens of thousands of years to reach even the closest stellar neighbors. The Voyager probes, launched decades ago, are still barely scratching the edge of our solar system's influence. We live in what amounts to a cosmic island, cut off from the rest of the galaxy by barriers of time that make meaningful exploration seem impossible. Yet physicists continue to wrestle with concepts that might, someday, change everything. The theoretical frameworks of relativity suggest strange possibilities, wormholes through spacetime, regions where the normal rules might bend, exotic matter with properties we can barely imagine. These ideas remain firmly in the realm of speculation, but they hint at something profound about the nature of reality itself. If such barriers could ever be overcome, the transformation wouldn't be gradual or subtle. It would represent a fundamental shift in what it means to be human. Throughout our history, every breakthrough in transportation has reshaped civilization completely. When our ancestors first learned to sail across oceans, they didn't just reach new lands, they created new ways of thinking about the world. The invention of the wheel changed how we organized settlements. Ships connected continents and mixed cultures in ways that created entirely new forms of art, language, and philosophy. Railways compressed geography, making distant cities feel like neighbors. Aviation turned the planet into something you could circle in hours Rather than years, each leap forward in mobility has triggered cascades of change that rippled through every aspect of human society. Trade networks formed along new routes, ideas spread faster, isolated populations suddenly found themselves part of larger conversations. The same pattern has repeated itself countless times throughout history. Now imagine applying this same principle to the stars themselves. Journeys that currently exist only in science fiction could become routine commutes. Star systems separated by light years might start to feel like distant continents once felt to explorers centuries ago. The psychological shift alone would be staggering. Children growing up in such a world would think about their futures differently. Career choices might include working on planets orbiting distant suns. The concept of emigration could expand to include leaving one solar system entirely for another. What we consider impossibly remote would become simply far away. This would revolutionize our search for life beyond Earth. Right now, we're limited to studying other worlds through telescopes, analyzing the faint chemical signatures in starlight to guess at what might exist on planets we'll never visit. Robotic probes can reach nearby planets, but they take years or decades to arrive and can only send back limited information. Direct exploration would change everything. We could walk on the surfaces of worlds orbiting other stars, sample their atmospheres, dig into their soil, search for signs of biology with our own hands and instruments. The discovery of even simple microbes on another world would shatter our understanding of life's uniqueness. Such a discovery would force us to reconsider our place in the cosmic order. Life would no longer be a mysterious accident, confined to one small planet, but a phenomenon that emerges wherever conditions allow. This realization would ripple through philosophy, religion, and science in ways we can barely predict. Finding intelligent life would be even more transformative. The knowledge that consciousness has evolved elsewhere would challenge every assumption we hold about intelligence, culture, and meaning. We would no longer be alone with our questions about existence and purpose. But exploration represents just one dimension of change. Communication across interstellar distances currently faces the same cruel limitations as travel. Radio signals take years to cross the space between stars, making real conversations impossible. Messages sent to nearby star systems would receive replies only after decades had passed. This delay creates a profound isolation that shapes how we think about the universe. We can observe distant galaxies, but we cannot interact with them in any meaningful way. They remain frozen images from the past, beautiful but utterly separate from our experience. Faster forms of travel might enable new ways of carrying information. Physical messages could be transported, or perhaps the same technologies that allow rapid movement through space could also enable instantaneous communication. Networks of human settlements could maintain regular contact across previously impossible distances. Even if such communication weren't instant, reducing delays from years to days or weeks would create psychological bridges across the void. Colonies on distant worlds would no longer feel completely cut off from their origins. Cultural exchange could continue, despite physical separation. The economic implications would be equally dramatic. Resources found in other star systems could potentially be transported or traded. Entire industries might emerge around interstellar mining, manufacturing, or energy production. Rare elements abundant in one system, but scarce in another, could become the basis for new forms of commerce. Imagine asteroid belts rich in platinum, gas giants perfect for harvesting helium isotopes, or worlds covered in materials that don't exist naturally on Earth. The economic geography of human civilization could expand to encompass dozens or hundreds of star systems, each contributing unique resources to a vast interstellar network. This raises fascinating questions about governance and law. How would agreements be enforced across such distances? What authority could regulate trade between worlds separated by light years? The challenges of managing a global economy pale in comparison to coordinating commerce across multiple solar systems. History suggests that separation often leads to divergence. Communities isolated by geography develop distinct languages, customs, and traditions. Star systems separated by even greater distances might evolve their own unique cultures over time, gradually becoming less recognizably human as centuries pass. This cultural evolution could be accelerated by the need to adapt to different environments. Humans living on high-gravity worlds might develop different physical characteristics. Those inhabiting space stations could evolve distinct social structures. The psychological effects of seeing unfamiliar constellations every night might influence art, religion, and philosophy in unpredictable ways. Yet this same diversity could become a source of strength. Multiple human societies spreading across the galaxy would serve as a kind of insurance policy for our species. Natural disasters that could threaten life on Earth, asteroid impacts, supervolcanic eruptions, or long-term changes in our sun's behavior would no longer pose existential risks to human civilization as a whole. The concept of dispersing life across multiple worlds has deep philosophical appeal. It represents a form of cosmic gardening, spreading the complex chemistry of biology to places where it might never have emerged naturally. Earth's evolutionary experiments could be preserved and continued even if our home planet faced catastrophic changes. But such dispersal would also carry profound risks. The same technologies that enable interstellar travel could potentially be weaponized. The ability to move quickly between star systems might create conflicts on scales never before imagined. Managing such power responsibly would require new forms of international cooperation and oversight. Environmental concerns would also multiply. Every new world visited would raise questions about preservation and contamination. Should we protect alien ecosystems from human interference? How do we balance scientific curiosity with environmental responsibility? These dilemmas already challenge our exploration of Mars and other bodies in our solar system. There's something deeply moving about contemplating these possibilities. The stars that have inspired human wonder for millennia might someday become destinations rather than distant lights. The night sky itself would take on new meaning, no longer just a beautiful backdrop, but a map of reachable places. This transformation would likely unfold gradually, rather than suddenly. Early interstellar missions might carry only small probes or specialized equipment. Progress would probably be slow, expensive, and uncertain, much like the early days of aviation or spaceflight. Even revolutionary technologies face practical limitations and unexpected challenges. The universe would never feel small, no matter how fast we learn to travel through it. There would always be new regions beyond our reach, new mysteries waiting at greater distances. The cosmos operates on scales that humble human ambition, reminding us that we remain small players in an incomprehensibly vast story. Perhaps that's the most profound aspect of imagining such futures. They connect our daily concerns to the longest possible timescales, the gradual evolution of stars, the slow dance of galaxies, the patient unfolding of cosmic history itself. Whether or not we ever travel faster than light, we remain part of something much larger than our individual lives. The stars continue their ancient burning, regardless of our hopes and dreams. They offer both inspiration and perspective, reminding us that the universe contains wonders we've barely begun to explore. In contemplating the possibility of reaching them, we glimpse something eternal about the human desire to push beyond boundaries, to seek new horizons, to never stop asking what lies just beyond our current understanding. In cultures around the world, ancient stories carry warnings that feel surprisingly modern. Tales of Icarus flying too close to the sun, of Pandora opening forbidden boxes, of travelers moving so fast they lose themselves along the way. These weren't really stories about flying or speed. They were about what happens when power grows faster than understanding. When we think about faster than light travel today, even in the realm of pure imagination, the same ancient questions quietly surface. Sure, there are massive engineering challenges, energy requirements that boggle the mind, physics problems that may never be solved, but underneath all that lies something deeper. A question that would remain even if we cracked every technical puzzle. Should we actually do it? Our first instinct might be obvious, of course we should. Humans have always been explorers. We crossed continents when they seemed impossibly vast. We sailed oceans when people thought you'd fall off the edge. We launched ourselves into space when it was nothing but science fiction Each generation pushes further than the last. Faster than light travel would just be the next chapter in this very long book. But speed doesn't just change distance. It changes everything else too. Relationships shift when you can be somewhere instantly. Timing becomes different when travel takes no time at all. Decision-making transforms when the whole universe suddenly feels close enough to touch. Think about how the telegraph changed everything in the 1800s. Messages that used to crawl across oceans in wooden ships suddenly zipped across continents in minutes. Businesses could coordinate like never before. Governments could react instantly to events on the other side of the world, but life also got faster, more pressured. People had to make decisions quickly, sometimes without enough time to really think things through. The telephone did it again. Radio pushed the pace even more. Television, then the internet, each one compressing time and distance in ways that seemed impossible just decades before. And each time, society had to scramble to keep up, not always successfully. If faster-than-light travel ever became real, we'd see this pattern amplified beyond anything in human history. Entire star systems could become as connected as neighboring cities. The universe would shrink in ways that might make our heads spin. History tells us something important about rapid change. People don't always adapt easily. Cultures need time to absorb new realities, to figure out how to live with technologies that reshape everything. When change happens too fast, societies sometimes crack under the pressure. Not because progress is bad, but because speed itself isn't always an unqualified good thing. There's also the question of responsibility floating in the background. If we could hop between stars like we currently hop between continents, we'd have access to worlds that have been evolving independently for billions of years. Every planet represents a unique experiment in natural history. Processes that formed over unimaginable timescales, creating environments that may never happen again in exactly the same way. Would we have the right to change these places? Should untouched worlds be left alone, studied from a distance, or opened up for settlement? These aren't scientific questions with clear answers. They're ethical puzzles that don't have neat solutions. We're already having smaller versions of this debate about Mars and other places in our solar system. Some scientists say we should avoid contaminating other worlds with Earth life, just in case native microorganisms exist there, or existed there once. Others argue that exploration and settlement are natural expressions of human curiosity, part of our basic survival instinct. Faster-than-light travel would scale this debate up dramatically. The number of reachable worlds would explode. The consequences of human activity would stretch across vast regions of the galaxy. Then there's the unpredictability factor. Human exploration has a track record of bringing changes that nobody saw coming. When cultures meet, ideas spread, technologies transfer. Sometimes diseases travel too. Entire civilizations have been transformed by what started as simple voyages of discovery. If humanity encountered other forms of life out there, whether simple microbes or complex civilizations, the effects could ripple through our society in ways we can't even imagine. Even just knowing for certain that other intelligent life exists could reshape philosophy, religion, politics. Changes that might unfold over generations, touching aspects of human culture we never expected. There's something philosophical about distance itself that's worth considering. Throughout most of human history, distance has created natural limits that shape how communities develop. Travel takes time, and that time creates rhythms. Journeys require preparation, thought, commitment. Physical separation allows cultures to grow in different directions, to develop their own character. If faster-than-light travel dramatically reduced those separations, the whole character of human experience might shift. The sense of remoteness, of being far from other places, could fade away. The universe might start to feel smaller, more connected, but also somehow more crowded. Some people would probably love that change. Others might feel like something precious had been lost. The quiet that comes with distance. The patience that long journeys require. The feeling that some places are truly, genuinely far away. Any technology powerful enough to move things rapidly across vast distances could potentially be used for purposes other than peaceful exploration. The same capabilities that enable wonderful journeys could be turned toward conflict. The faster and more powerful a technology becomes, the more crucial it is to make sure it gets used wisely. This concern isn't unique to faster-than-light travel. It shows up with nuclear energy, with artificial intelligence, with any sufficiently powerful tool. The challenge is always the same. How do you balance innovation with responsibility? How do you pursue what's possible while also considering what's beneficial in the long run? Some philosophers suggest that technological progress should be guided not just by what we can do, but by what we should do. This requires thinking beyond immediate advantages, considering broader effects on society, on the environment, on future generations who will inherit whatever we build. It's worth asking why we want to travel faster than light in the first place. Is it purely about exploration? Or is there also a deeper desire to overcome limits, to prove that no boundary can contain us? Ambition and curiosity aren't bad things. They've driven many of humanity's greatest achievements, but there's also value in recognizing that some limits aren't just obstacles to overcome. They're features of how the universe actually works. The speed of light, for example, shapes how galaxies evolve, how stars shine, how cause and effect unfold across space and time. It's not just a barrier to travel, it's part of the deep structure of reality. Maybe the universe isn't meant to be crossed instantly, but experienced gradually. Maybe distance and time aren't just inconveniences, but elements that give journeys their meaning. Walking across a landscape feels completely different from suddenly appearing at your destination. The passage of time allows for anticipation, observation, change. The journey itself becomes part of what makes it worthwhile. This doesn't mean faster travel is inherently undesirable. Few people would choose to go back to crossing oceans in wooden ships, facing storms and uncertainty for months. But it does suggest that speed alone isn't the only measure of progress. Even if faster-than-light travel became real, it might not eliminate the need for patience. The universe is so incredibly vast that even traveling faster than light would leave enormous distances still beyond reach. There would always be horizons farther away, mysteries not yet explored. The desire to go faster might never be fully satisfied. Each new capability would reveal new frontiers. If humans begin living on many worlds, separated by light years, what would it mean to be human? Would there be a shared culture connecting all these distant colonies? Or would different settlements develop their own languages, traditions, ways of thinking? Distance, even when it can be crossed quickly, tends to create differences over time. Environments shape societies in subtle but powerful ways. A community living on a world with lower gravity, different day lengths, different atmospheric conditions, would probably develop customs and technologies unlike those on Earth. Faster-than-light travel might allow visits and exchanges between worlds, but it might not prevent this kind of divergence. Humanity could become a family of related cultures rather than a single unified civilization. Some might see that as a loss of unity. Others might see it as richness, a diversification of human experience across the galaxy. For individual travelers, the ability to cross vast distances quickly might be thrilling, but also deeply disorienting. Moving between worlds, seeing different constellations in alien skies, knowing that home lies impossibly far away, these experiences would probably change how people think about their place in the universe. Astronauts who've seen Earth from orbit often describe a shift in perspective, sometimes called the overview effect. Seeing our planet as a small, fragile sphere against a darkness of space creates a sense of unity and responsibility that's hard to shake. Interstellar travel, especially at speeds that make distant stars accessible, might deepen this perspective even further. Earth would no longer be the center of human activity, but one world among many scattered across the galaxy. That realization might bring a profound sense of humility, a recognition that humanity is part of a much larger cosmic story than we usually think about. All of these reflections remain purely speculative, of course. faster than light travel hasn't been achieved, and may never be. The philosophical questions surrounding it are preparations for a future that may or may not arrive. But there's real value in asking such questions now. They push us to think carefully about the relationship between knowledge and wisdom, between what we're capable of doing and what we're responsible for doing. The question isn't only whether we can go faster than light, but what kind of civilization we'd want to be, if we could. The cosmos operates on timescales that dwarf human understanding, and there's something profoundly reassuring about this reality. Stars burn for billions of years, following the same nuclear processes that have illuminated the universe since its earliest epochs. When we observe distant galaxies through telescopes, we're seeing light that began its journey long before Earth had formed its current atmosphere. This ancient light carries information across unimaginable distances, never rushing, never deviating from its steady path through space. Light itself moves at what we call the speed of light, roughly 300 million meters per second, but even at this incredible velocity, it takes years to reach us from the nearest stars. From the star Proxima Centauri, light needs over 4 years to complete its journey to Earth. From more distant regions of our galaxy, light travels for thousands or even tens of thousands of years before reaching our instruments. The photons hitting your eyes right now from distant stars are older than recorded human history. Space between celestial objects isn't truly empty, though it might appear so at first glance. The regions between stars contain sparse clouds of hydrogen gas, cosmic dust particles, and occasional molecules that drift through the interstellar medium. These materials are incredibly dilute, far less dense than the best vacuum we can create in laboratories on Earth. Yet over vast distances, even this thin material plays important roles in stellar formation and galactic evolution. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars, each following its own orbital path around the galactic center. This massive stellar collection rotates as a whole, but so slowly that one complete rotation takes approximately 225 million years. Dinosaurs lived during Earth's previous position in this galactic orbit. The spiral arms we see in photographs of other galaxies are not fixed structures, but rather density waves that compress gas and trigger star formation as they move through the galactic disk. When astronomers study the possibility of faster-than-light travel, they encounter fundamental barriers rooted in the structure of spacetime itself. Einstein's theory of relativity shows us that space and time are interwoven into a single fabric, and this fabric has properties that limit how information and matter can move through it. As objects approach light speed, their mass effectively increases, requiring ever more energy to accelerate them further. Reaching light speed would require infinite energy, making it impossible for any object with mass. Some theoretical physicists have proposed exotic solutions like warp drives, which would compress space in front of a spacecraft while expanding it behind. These concepts don't violate relativity because they manipulate space-time itself, rather than moving through it at prohibited speeds. However, such technologies would require forms of matter and energy that may not exist in nature. Negative energy densities, exotic matter with unusual properties, these requirements push far beyond our current understanding of physics. Wormholes represent another theoretical possibility for covering vast distances quickly. These hypothetical tunnels through space-time could potentially connect distant regions of the universe, allowing travel between them without crossing the intervening space. Yet wormholes, if they exist at all, would likely be incredibly unstable, collapsing almost immediately, unless held open by exotic matter we've never observed. The energy requirements for any form of faster-than-light travel dwarf anything humanity has ever produced. Some calculations suggest that warping space around even a small spacecraft would require energy equivalent to the mass of entire planets or stars. Converting matter to energy with perfect efficiency, as Einstein's famous equation describes, still wouldn't provide enough power for most proposed faster-than-light technologies. Current space exploration proceeds at a much more measured pace, and there's beauty in this gradual approach. Robotic spacecraft have crossed the boundaries of our solar system, carrying messages and artifacts that represent human culture. These probes move at speeds that seem impossibly slow compared to light. Yet they've revealed details about distant worlds that would have been pure speculation just decades ago. The Voyager spacecraft, launched in the 1970s, are now traveling through interstellar space, having left the influence of our sun's solar wind behind. They carry golden records containing sounds and images from Earth, just in case some future civilization encounters them. These silent ambassadors will continue their journeys long after the people who built them have been forgotten, drifting between the stars for millions or billions of years. Even without faster-than-light travel, we're already exploring the universe in remarkable ways. Radio telescopes detect signals from objects billions of light-years away. Space-based observatories study the heat radiation from the cosmic microwave background, remnant energy from the Big Bang itself. Gravitational wave detectors sense ripples in spacetime caused by colliding black holes and neutron stars, events so violent they distort the fabric of reality. These gravitational waves travel at light speed, carrying information about some of the most extreme events in the cosmos. When massive objects accelerate or collide, they create waves that spread outward through spacetime itself. The waves are incredibly weak by the time they reach Earth, causing distortions smaller than 1,000th the width of a proton. Yet sensitive instruments can detect these tiny changes, opening an entirely new window for astronomical observation. Black holes represent some of the most extreme environments in the universe, regions where gravity becomes so intense that nothing, not even light, can escape once it crosses the event horizon. Near a black hole, time itself slows down relative to distant observers, an effect predicted by relativity and confirmed by precise measurements. If you could somehow survive approaching a black hole, time would pass normally for you, but observers far away would see your movements becoming slower and slower as you approached the point of no return. The expansion of space itself adds another layer to cosmic distances. Galaxies aren't just moving through space, they're being carried apart by the expansion of space between them. The most distant galaxies we can observe are receding from us at velocities that approach light speed, not because they're moving that fast through space, but because space itself is stretching. Light from these distant objects becomes stretched as well, shifting toward redder wavelengths in a phenomenon called cosmological redshift. This expansion means that even if we could travel faster than light, the universe would still present infinite frontiers. New regions would constantly move beyond our reach as space continued expanding. The observable universe has a definite edge, not because space ends there, but because light from more distant regions hasn't had enough time to reach us. Since the Big Bang occurred roughly 13.8 billion years ago. Within our own solar system, the distances are more manageable, but still impressive by human standards. Sunlight takes about 8 minutes to reach Earth, which means we always see the sun as it was 8 minutes in the past. Light from Jupiter takes between 33 and 54 minutes to reach us, depending on the positions of the planets in their orbits. Radio signals sent to spacecraft exploring the outer solar system face these same delays, making real-time control impossible for distant missions. The concept of simultaneity becomes complex when dealing with such distances and the finite speed of light. Events that appear simultaneous from one perspective may occur at different times when viewed from another reference frame. This isn't just a theoretical curiosity, it affects practical technologies like GPS satellites, which must account for relativistic effects to maintain accuracy. Quantum mechanics introduces additional mysteries about the nature of information and causality. Quantum entanglement allows particles to share correlations that persist regardless of the distance separating them, leading to what Einstein called spooky action at a distance. However, these quantum correlations cannot transmit information faster than light, preserving the causal structure of spacetime while still permitting genuinely strange phenomena. The relationship between energy and matter, expressed in Einstein's equation, E equals mc², reveals the enormous energy content locked within ordinary matter. The fusion reactions powering stars convert only a small fraction of matter into energy, yet they sustain stellar luminosity for billions of years. The complete conversion of matter to energy would release far more power, but achieving such conversion remains beyond our technological capabilities. Antimatter represents the closest thing we have to perfect energy conversion, with matter-antimatter annihilation converting mass entirely to energy. However, producing and storing antimatter requires enormous resources, and naturally occurring antimatter is extremely rare in our region of the universe. The energy cost of creating antimatter far exceeds the energy we can extract from it using current methods. These physical constraints don't diminish the wonder of cosmic exploration. They simply channel it in different directions. Understanding why faster-than-light travel is difficult teaches us about the fundamental structure of reality. The speed of light isn't just a speed limit for moving objects. It's the speed at which cause and effect propagate through the universe, the speed at which information can travel from one location to another. This universal speed limit creates a kind of cosmic present, a sphere expanding outward from any given point at light speed, defining which events can influence each other and which remain causally disconnected. Beyond this light sphere, events are happening right now that cannot yet affect us, and will not be able to do so for years, centuries, or millennia, depending on the distances involved. The patient pace of cosmic processes offers a different perspective on time itself. While human life unfolds over decades, stellar evolution occurs over millions or billions of years. Galaxies merge over even longer timescales, their gravitational dances playing out across cosmic epochs. This vast temporal landscape puts daily concerns into a broader context, suggesting rhythms of existence far more gradual than our immediate experience. Yet within these enormous scales, intricate details emerge at every level of magnification. Individual stars host planetary systems with their own complex dynamics. Planets develop geological processes, atmospheric circulation patterns, and sometimes conditions suitable for life. Even in the apparent emptiness of interstellar space, complex chemistry occurs as molecules form and react in the cold, sparse environment between stars. The search for life elsewhere in the universe proceeds without requiring faster-than-light travel. Radio telescopes listen for artificial signals from other civilizations. Spacecraft study potentially habitable worlds within our own solar system. Ground-based observatories analyze the atmospheres of planets orbiting other stars, looking for chemical signatures that might indicate biological processes. These investigations remind us that exploration can take many forms, not all of which require physical travel. Understanding distant environments through electromagnetic radiation, gravitational effects, and other phenomena provides genuine knowledge about places we may never visit directly. The information carried by light reveals temperatures, chemical compositions, motions, and physical processes occurring in the most remote corners of the observable universe. Each photon reaching our instruments carries a small piece of this cosmic story, having traveled across space for periods that may span significant fractions of the universe's entire history. When we detect light from very distant galaxies, we're seeing them as they existed when the universe was much younger, providing direct observational access to cosmic evolution over billions of years.